This course will take you from zero to mastering Prometheus. We're going to start with module 0, which is setting up Docker and Kubernetes on your local machine. This prerequisite step will prepare you for the remaining 9 modules of this course, where the first 3 require a Docker Compose environment, and the last 6 require a Kubernetes environment. We can now begin with module 0. If you already have Docker and Kubernetes set up on your local machine, you can skip to this timestamp. If not, I'm going to play a video from my Kubernetes course that shows how to set up Docker and Kubernetes on your local machine. Enjoy. Now we're going to install Docker. So write Docker install inside of Google, install the Docker engine. I'm using a Mac. If you're using a MacBook that has the M1, M2, or M3 chip, whatever, click on Docker Desktop for Mac with Apple Silicon. If you're still using a Mac with the Intel chip, click on that. I'm going to click on this one. I already have Docker installed, but I'll just go through the process with you. It's actually fairly simple. So go to my downloads, click on the installer. It should install right away. It's just going to prompt you to drag this to your applications folder. All right. If I open up the Launchpad, I'm going to see Docker right here. If I click on it, I already have the Docker engine started up and running. For you, it should show a whale icon that's just starting up. Give it some time to start up. Okay, once it shows Docker Desktop running, click on Sign In/Sign Up. All right. Then I'm going to continue with Google because I already have an account with them. If you don't have an account, make sure to sign up and then sign back in. All right. So I'm going to continue with Google. It's going to sign me in. Now I can open Docker. So this is the Docker dashboard, and it shows that I'm signed in as rslim087. Please do not proceed with this course until you have a Docker account and that you're signed into it through your local Docker dashboard, okay? You can access the dashboard all the same by just clicking on Go to Dashboard. Again, make sure it shows your username, make sure you're logged in. Once you have that set up, this is where all of our containers will show up. We're gonna have visibility to them there. Well, we're also gonna access them through the command line, but whatever. You can also see your image. All right, hey guys, it's Rand from the present. Click on the gear icon in your Docker dashboard, okay? Once you do that, go to Kubernetes, click Enable Kubernetes, Apply, and Restart. Okay, should take a bit of time, not too long. All right, once it stops loading, you've enabled Kubernetes, and what this does, it starts a single node. Now that we have our environment ready, let's begin module 1, where we're going to set up Prometheus and Grafana in Docker Compose to monitor a web application. I'm going to play the video now. Enjoy. So what we're going to be doing is we're going to run Prometheus and Grafana inside of a Docker Compose environment. We're going to use these technologies in order to monitor a containerized Flask application that's exposing different types of metrics at a particular endpoint. So these could be counter metrics, gauge metrics, histogram metrics. Essentially, what we have is an application that's been instrumented to expose metrics in a format that Prometheus can understand. And so what we're going to do is orchestrate our Docker Compose environment in such a way where Prometheus is configured to scrape these metrics in 15-second intervals. So once we ensure that this data, this application's metric data, is always being saved inside of the Prometheus database and regularly being kept up to date every 15 or 20 seconds, Then we can use Grafana to query all of the metric data inside of Prometheus, and based on these queries, create insightful visualizations that give us a clear picture of how the application is performing in real time. All right, so I pushed all of the configuration files you're going to need inside of the following GitHub repo. I left you a link in the video description that you can use to access this repo. Click on the link. Once you're there, grab the URL that we can use to clone this repository inside one of the folders in our local machine. It doesn't really matter. But just make sure you know where this repository is being cloned. That way you can launch it inside of an editor of your choosing. I'm going to be using Visual Studio Code. Spin up a new terminal that points directly to my project where I can simply run docker compose up. So what that's going to do is spin up a Docker Compose environment that creates a container called Fast API app out of a Fast API image. So I lied. We're not going to be running a Flask app that exposes metrics. We're going to be exposing a Fast API app that exposes metrics, but doesn't really matter. They all expose metrics in a way that Prometheus can understand. We're going to be creating a Prometheus container from the Prometheus image and a Grafana container from the Grafana image as well. Okay, now this Fast API app, I programmed it to expose metrics at the path/metrics, all right? And it runs on the port 8000. So this Prometheus instance, what it needs to do is try to discover this Fast API application running on port 8000 and scrape its metrics at the path/metrics, okay? How are we going to configure Prometheus to discover this endpoint and regularly pull metric data from it? Well, this is where the volumes field comes into play, because volumes, what it allows you to do is grab a file from your local machine and load it into your container. So we're going to be loading the prometheus.yaml file into the Prometheus container because it contains the configuration that Prometheus is going to use in order to determine which app it needs to scrape metric data from. In this case, it's going to find the Fast API app container, connect to it at port 8000, all right, and then it's going to look at its path/metrics and scrape all of the data from it. All right. And it's going to do that every 15 seconds. So what is the data going to look like that Prometheus will scrape? Let's just go ahead right now and go to localhost 8000. All right. So us from our local machine, we can access the Fast API app at localhost 8000, but Prometheus, because it's running within the same Docker Compose network, it's going to access this app using the container name port 8000/metrics, okay? So if I go to localhost 8000/metrics from my end, I'm going to see all the metrics that our Fast API app is exposing. So here we see a histogram metric where the HTTP request duration can be split into different buckets. Do we see a counter metric anywhere? Here we see a counter metric, the total HTTP requests. Do we see a gauge metric anywhere being exposed by this app? Here we see a virtual memory bytes metric. That is a gauge metric as well. Okay, pretty cool stuff. So I instrumented this Fast API application using the instructions that you can find inside of this article that is inside of the video description. So if you're curious about how different types of apps can be instrumented to provide metrics, make sure to check out the articles, okay? We don't necessarily care about that because right now, Prometheus is configured to scrape these metrics every 15 seconds. How are we going to determine that? Well, let's access our Prometheus instance from our local machine using localhost 9090. Let me do that over here. Localhost 9090. There's Prometheus. All right. Is it pulling this data? Let's make sure. What we can do is a very simple query is copy one of these metrics directly into our PromQL editor, press execute, and the fact that we get results means we are golden. It's saving all of this data inside of its database. Let's try this one as well. That one is being saved as well. It is simply 0. Another way to verify is to go to status, go to targets, and you can see that the Fast API app at port 8000/metrics, this app over here is indeed a target that's being discovered by our Prometheus instance. All right. And so now we've got all of this data inside of Prometheus. How can we get Grafana to query the Prometheus data source and create insightful visualizations from these queries? So here we have Grafana set up, and in it, we're giving it an environment variable that essentially determines what the password to access the Grafana console will be. So by default, the username is admin. We're making the password admin here as well. So let's go to localhost 3000, okay, to access Grafana. We can log in with the email admin, password admin. You can ignore these because I was playing around with it earlier. We don't want to give it a new password. Just skip. No thanks. And now what we're going to do is we're going to click on settings. Where is that? Oh, there it is. Click on settings, data sources. We want to add a data source from which Grafana can query data from. We have a Prometheus data source that's running inside of the same network as Grafana. So we can safely say, look for a Prometheus data source, okay? And because Grafana and Prometheus are running inside of the same Docker Compose environment, it is able to access Prometheus using the container name followed by the port. So Prometheus 9090, while we would access it using localhost 9090, the container inside of the same Docker Compose network would rely on the container name followed by the port. Let me just make sure I got the name right. Prometheus 9090. Oh, don't forget your HTTP. Okay, and that's pretty much it. Save and test. Data source is working. We're able to perform PromQL queries against Prometheus. So we're not actually going to go through the queries ourselves because PromQL is in the last lesson of this series. Make sure to subscribe so that you don't miss out on it. But what I have is a Grafana dashboard already set up over here that already contains all of the PromQL queries in it. So we can import this dashboard, load it in, import, and there you go. It's actively querying the data inside of our Prometheus database and allows us to visualize the request rate, the average response time, the memory usage, and the CPU usage of our Fast API application. Let's move on to module 2. So now we have metric data inside of Prometheus, and Grafana is querying this data, allowing us to visualize it. Now behind each panel in this Grafana dashboard was a PromQL query. It follows that in order to learn how to create effective Grafana dashboards, you need the Prometheus query language PromQL. I'm going to play the video now. Enjoy. You've got Prometheus collecting all of this metric data, and we can make sense of all that data by making queries to it using the Prometheus query language PromQL. In this lesson, you're going to master PromQL. You're going to start from very simple metric queries and build your way up to production grade monitoring. So let's not waste any time and dive right into it. Chapter 1, we're going to get started. It's going to be a very quick chapter because I already have. And so it only makes sense that in Chapter 2, we seek to understand all of the different metric types before we perform any queries on them. Okay, so at this endpoint, I've got a Python application that is exposing many metrics. And in the back end, Prometheus is scraping all of these metrics every 20 seconds. And ahead of each metric, there are two comments. a help comment that describes what the metric is, and a type comment that defines the type of metric that we're dealing with. Okay, the three most common types of metrics that you'll ever encounter are counter metrics, gauge metrics, and histogram metrics. We'll start by discussing the counter metric because it's used for measurements that can only ever go up. One such measurement is the total number of HTTP requests made on a particular path. So here we're tracking the total requests made on the path/metrics. So far we've got 3, but if I refresh the page, it should increase because Prometheus behind the scenes is actively making requests at this path in order to scrape all of this metric data. Okay, but let's look at some more interesting output. What if I make a request to the application's homepage at localhost 8000? I'm going to make 4 more requests, so 2, 3, 4, 5. Refresh the metrics page, and now I see over here that 5 requests were made on the path/. And so that's the thing with labels. They add dimensionality to your data. For the same metric, we have 2 different measurements, one that tracks the total number of requests made on the path/metrics, and one that tracks the total number of requests made on the path/. The second metric type that is very common is the gauge metric, and a gauge metric is one that goes up and down very frequently. One such metric that is most common is the CPU usage, because CPU usage, as you all know, goes up and down depending on the amount of workload, depending on the amount of traffic that the application needs to handle. Okay? And the third type of metric that is very, very common is the histogram metric. A histogram metric is ideal for measuring request duration because it's a metric that just needs to be distributed into many buckets. Why? Well, if I just told you that most requests made on the path/ took 5 milliseconds on average, that doesn't really tell me much. What I want instead is a distribution that tells me how many requests took less than 5 milliseconds, how many requests took less than 10 milliseconds, so on and so forth. Okay? So here, out of all 5 requests that I made on the path/, 3 requests took less than 5 milliseconds. The bins are cumulative. 1 more request took less than 10 milliseconds. And here, 1 more request took less than 25 milliseconds. And because the bins are cumulative, I can ignore the rest. So now here I can say that most requests fall inside of this bucket. Most requests are taking less than 5 milliseconds, which means my application is pretty healthy and processing requests very, very quickly. All right, so that's all for the different metric types. All of this metric data is being regularly scraped by Prometheus every 20 seconds and saved into the Prometheus database. I can access the data being saved into the Prometheus database through the Prometheus UI, which, based on my setup, is in localhost 9090. If you have the same setup as me, feel free to go there because we're going to be querying the data inside of the Prometheus database. And because we know all of these metrics are in Prometheus, the simplest type of query we can make is just by pasting in the metric itself. And if we execute this query, what that's going to do is display all of the metrics, all of the measurements that match HTTP request total. Here we see the number of requests made on the path/, and here we see the number of requests made on the path/metrics. Okay? And now what I'm going to do is something called label selection, essentially filtering our output to only include the metrics that match the labels we're filtering by. I'm just going to filter our output to only include metrics that have the label path/. Okay? And there you go. And now, in the interest of introducing more variety into our metric data, what I'm going to do, if you have the same setup as me, feel free to do what I'm about to do. If you don't, no worries, just follow along. you should have a collection.json file inside of your workspace. What I want you to do, if you have the same setup as me, is open Postman or download it from the web if you need to, and then import this JSON collection into it. What that's going to allow you to do is make requests to your Python web application. We can make requests at the root path. We'll make 2 more requests. That should take us to 7. Let me make sure. All right. We'll make, let's say 4 post requests. 1 get request on the path /items /1. We'll make 3 get requests. Why not? We'll make some put requests. We'll make 1 delete request. And that's good enough. Let's refresh what we've got. So now we've got a variety of metrics being exposed by our Python web application. I'm going to wait a little bit to allow Prometheus the chance to scrape this data and save it into its database. It should have saved it by now. So now what I'm going to do, I'll start by removing the filter. Okay, here we see all measurements that match this metric. And now what I can do is apply a filter that says only include the measurements that are actually get requests. So my label is going to be method equals get. And just note that labels are case sensitive. Okay, and now it only includes the measurements that have the following label. And I can even apply multiple filters and say only include metrics that have the label method get and the label path is equal to /. Beautiful. All right. Now something else I wanted to show you was regex matching, which is something that you can do in PromQL. So here I've got all of these metrics. One is a put request that is made on the path /items/1. One is a post request made on the path /items. One a get request. And now what if I want to retrieve all of the metrics whose path starts with /items? So what if I want to retrieve this measurement, this one, and this one as well? What I can do is the following. I'm going to say, grab me all the metrics, and here we have an option to use regex to match all paths that start with /items. Then we'll put a dot followed by an asterisk. All right, if I execute the following query, we get all the measurements whose path starts with /items. Okay, I can go even further and say, get all the ones that start with /items/1, and now I expect this one to get filtered out. And indeed it does. So you can use regex matching. And now let me remove the 1. And what I'll do is an anti-regex, a negative regex that says, don't include any paths that start with /items. And we get exactly that. Cool. Before we perform any more queries, it's really important to understand why Prometheus is known as a time series database. So if I go to the endpoint where my application is exposing data, here we see the most up-to-date value of each measurement, the most recent value. But behind the scenes, Prometheus has been scraping this data nonstop every 20 seconds. So while here we see the most recent value of each measurement, in Prometheus, each measurement would have its own time series, where each timestamp in the time series records its value at a specific point in time. If I perform a query without specifying a range, what that's going to do is return the most recent up-to-date value of each time series. This is called, the output is called an instant vector. If in my query I specify a range of 5 minutes, what that's going to do is return a range of 5 minutes for each time series. This is called a range vector. Let's have a look right now. So here we see an instant vector. where each value is the most recent one for each time series. Okay? If I specify a range of 5 minutes, then what we're going to see is a range vector that specifies what the value has been for the past 5 minutes. So in the past 5 minutes, I didn't make any requests to the path slash. It follows that it didn't change at any of the timestamps. But here, because Prometheus is scraping the data every 20 seconds, we see that it changes quite often. Every 20 or so seconds, Prometheus makes a request to the path slash metrics. So this is a range vector because we get a range for each time series, and this is an instant vector because it returns the most recent value of every matching time series. Simple as that. So I want to boil this down to two definitions. A range vector computes a range of values per time series, and an instant vector computes a single value per time series. Nothing more, nothing less. I want you to really internalize and understand these definitions as I go over to the Prometheus documentation and show you that there are many, many Prometheus functions, some of which can be applied on instant vectors, and other functions can be applied on range vectors. The function I'm looking for specifically is the rate function, which is a very, very common function that expects to receive a range vector. And what it does is on each range in the time series, it'll calculate a per second average rate of increase. Let me give you an example. If we feed the rate function a range vector where each range belongs to an HTTP request total measurement, then what it will do is for the time window of each range, it will calculate the average number of requests per second. That's what a rate is. It's the average number of something per second. In this case, we're dealing with requests. Okay? So if I go over here and I query the total number of requests made to the path slash and the total number of requests made to the path slash metrics, I haven't made any requests to this path in the past hour or so, but Prometheus consistently makes requests to the path slash metrics. We can verify this by viewing the data over the past 1 minute. Okay? So over the past 1 minute, the number of requests on this path didn't really change. And here we see each timestamp is a single point in time every 15 seconds, whereby Prometheus is making a single request to the slash metrics endpoint. So if a single request is being made to the slash metrics endpoint every 15 seconds, and the rate measures the number of requests per second within this window, I expect the average rate here to be 1 divided by 15, 0.06667, and I expect this one to return 0. Let's try it out. All right, and that's pretty much it for rates. Now, very commonly, people compare the rate function versus the iRate function. Let me go to it right now. So the iRate function is very similar to the rate function in that it expects to receive a range vector and it calculates the per second rate of increase in the time series, but it only does it on the last 2 data points. Okay, so while the rate function computes the average number of something per second over the entire time window, what iRate does is it only looks at the last 2 points within that time window, and it calculates the instant rate of increase between these 2 points. So in a scenario where the frequency of requests is consistent throughout the entire interval, we would see very similar results for rate and iRate. But in a scenario where everything is going fine, but in the last 2 data points, there's like a sudden increase. While this anomaly would be averaged out using the rate function, iRate would show this sudden spike, this sudden increase in traffic. Okay, now for HTTP requests, rate is usually very good, and we're going to stick to it. But there's something interesting I mentioned in that rate and irate can only be used with counters. So if I go over to rate, should only be used with counters and native histograms. What if I want to measure how fast my CPU is changing over time, because CPU is a gauge metric and we can't use the rate function on it? Well, you technically can, you're just going to get really, really weird results if you decide to do so. Well, what we can do is look at the documentation, and we'll find out that there is a delta function that also takes in a range vector. And for each time series, it will calculate the difference between the first and last value. And this one can only be used with gauges and native histograms, which means we can use it on a metric such as CPU usage, okay, or CPU temperature in this case. So let's actually just go ahead and use it right now. If I go over to my metrics over here, we see that there's one called process CPU usage. What I can do is get the process CPU usage over the last 5 minutes, if you will. And here I see timestamps every 15 seconds over the last 5 minutes that show me how CPU is increasing and decreasing over time. If I want to get the change in CPU between the first and the last value, what I can do is say delta, process CPU usage, and there you go. And we get a negative 0.21. So in the past 5 minutes, CPU has gone down by 0.21%. Now I'd like to talk about aggregation operators: sum, average, max, and min. All of these operators have one thing in common. They expect to receive an instant vector, and they'll aggregate every value in that instant vector into a single value. Let's look at an example. So I went ahead and populated my application with some data, right? And now here, this query, what it does is it produces an instant vector because it produces a single value per time series. What I can do is aggregate every value in this instant vector into a single sum. So the sum, this aggregation operator, is going to get this instant vector as an input and produce a single scalar value. I can get the average rate of all the requests all the same, aggregating all the values in the instant vector into a single average. I can get the maximum rate among all the values in the instant vector, and I can get the minimum rate among all the values in the instant vector, which of course is going to be 0. Okay? All right, now before I continue, what I want to do is go back and just try to create some metric data, okay? I'm going to send in some post requests. That keeps creating an item with an ID of 3. So we're going to keep getting an item with an ID of 3, okay? If you choose an item with another ID, different than the one your post request produced, you'll get an item not found. All right, I'm going to update the item with an ID of 3. Okay, we've created some data. Let's go back, rerun the rate function. Cool, we have a more varied amount of data for now. And now what I can do is something called grouping by a label. What this basically does is it aggregates the values in your instant vector depending on the label that they have, essentially producing another vector. Okay, so I can say sum by method. What this is essentially going to do is aggregate every single value that has the method delete, every single value that has the method get, post, and put. If we execute that, we get a vector with 4 values. Each is the result of aggregating all the values that had the method delete, the method get, the method post, and the method put. Because the output is a vector, we can go even further and aggregate all the results of this vector into a single scalar value, into a single sum. Okay, that's pretty much it. So sum by grouping by a label before aggregation produces a vector, and just summing, just using a basic aggregation operator, takes a vector and produces a scalar value. Simple as that. Now we move on to aggregation over time. So just like how simple aggregators take an instant vector and produce a scalar value, aggregation over time functions, they kind of go up a dimension wherein they take in a range vector and produce an instant vector as a result. The sum over time function, for example, takes an arrange vector and it calculates the sum of all values in that specified range for each time series, computing a single value per time series, an instant vector. The average over time function, same thing, takes an arrange vector and it calculates the average of all values in the specified range for each time series, producing a single value per time series, an instant vector. Okay, you've also got max over time, which calculates the maximum value in the specified range per time series. Min over time, that one kind of explains itself. Okay, so let's go ahead and look at an example. What I'm going to do is start by flooding the root path with some requests, just so we can see some data. Okay, and then I'm going to query the HTTP request total metric for the path equals /. And I want to look at the results in the past 1 minute. Let's make this 2 minutes. Okay, good enough. Now, if I do a sum over time, it's just going to sum the value at each timestamp. Okay, so that should be like 700 and something. Cool. If I do an average over time, it's going to get the average amount of requests in total in the past 2 minutes. That query makes a lot more sense than sum over time. Here we get 93 requests on average. If I do max over time, it'll get the maximum amount of requests in this time span, which is obviously 94. And the min over time, oh, we must have gone past the 2 minute mark. Now it's all 94. Let's do 3 minutes. If I do min over time now, we should get 90. Now, instead of just doing a single path, let's remove the label selector, and it calculates a minimum value in the specified range for each time series, producing an instant vector. If I do average over time, again, it originally took in a range vector. Let me just show you the range vector. It originally took in a range vector where each time series has a range of values, and it calculated the average of all values in the specified range for each time series, producing an instant vector. Pretty cool stuff. That's it for aggregation over time. All right, now we're ready to perform queries on histogram metrics. So here we have a histogram distribution for the request duration on the empty path. And this tells us that some number of requests took less than 5 milliseconds, some number of requests took less than 10 milliseconds, some number of requests took less than 25 milliseconds, so on and so forth. But just now looking at the raw data itself isn't very insightful from first glance. It would be very useful if there was some function in Prometheus where we could just give it all of the histogram data, as well as the percentile, where we can ask, hey, given this request duration distribution, how fast were 95% of my requests? How fast were 50% of my requests? And then it spits out a number. Well, that function is called histogram quantile, and we're going to look at it now. So if I go to my raw metric data as it's being fed into Prometheus, we've got many histograms. The one we're going to focus on is the following, which measures the request duration made on the empty path / 17 requests took less than 5 milliseconds, 21 requests took less than 10 milliseconds, so on and so forth. So now what I want to do is output that same histogram onto my Prometheus UI using PromQL. So I'm only going to query the buckets that belong to the path /. Okay, let me fix that up. Classic label selection, press execute. My computer froze. There you go. So here we see the exact same thing. 17 requests took less than 5 milliseconds, 21 requests took less than 10, so on and so forth. Now, in order for this data to be fed into the histogram quantile function, the only label that it can have is the less than or equal to label. I have to somehow remove all of these. A workaround to this is to group each time series using the LE label. Because the LE label is distinct for each value over here, it follows that we're going to have the exact same number of groups as there are time series. So I'm going to wrap this up into brackets, group everything using the label LE. And because there's exactly one group for every time series, it doesn't really matter which aggregation operator we use. It could be sum by LE. It could be average by LE. Min by LE. Max by LE. You get the point. Let's just use sum. Okay. And now that we've got the buckets in this form, I can now feed it into the histogram quantile function. Histogram quantile. And now what I can tell the histogram quantile function is, hey, given this distribution of data, can you calculate how long 95% of my requests took? And this tells you that 95% of my requests took less than 22.7 milliseconds. Pretty darn cool if you ask me. Now what I'm going to do is go to Postman and make a lot of requests to the empty path. I'm going to make at least 10. Now 95% of requests took less than 16 milliseconds. I can change the percentile to 50. And this tells you that 50% of requests took less than 3 milliseconds. So I hope you can see how the histogram quantile function allows us to extract very valuable insight from our histogram distribution. In this chapter, you're going to learn how to compute meaningful averages and totals. A very common average to compute is the average number of seconds that a request takes to process. And the way to calculate this is to take the rate at which the duration of all requests is increasing per second and divide that by the rate at which the total number of requests is increasing per second, and that will yield the average number of seconds that each request takes. So here we've got many histograms, and after each histogram, there are two measurements. The first one is the total number of requests, and the second one is the total time spent on all requests. So here you can see we've got 36 requests that took less than 5 milliseconds, 41 requests that took less than 10 milliseconds. If you get the total time spent by all these requests, you would get this number right over here. And so if I want to get how long each request took on average, and the way to do that is first, let's grab the total time spent by all requests to process on the path slash, and let's view it as a range in the past 5 minutes, okay? So I haven't made any requests in a while, which means if I apply a rate function on this, I'm just going to get 0 because the request duration hasn't really changed in the past 5 minutes. So let me go to Postman, make a lot of requests on the empty path. Okay. And let's bring this window down to 2 minutes. We'll give Prometheus a chance to scrape the metric data. It hasn't done so yet. So here we can see that things have changed. Has it changed in Prometheus yet? All right. So now what I'm going to do is take the rate at which the request duration has been increasing in the past 2 minutes and divide that by the rate at which the total number of requests made on this path has been increasing in the past 2 minutes. So we'll just copy this over. And this gives me the average time that it takes for each request to process on this path. Simple as that. And now let's talk about totals. A very common total to calculate is the total requests over time. And Prometheus provides a very handy function in order to do that. And that is a function known as the increase function. So the increase function expects a range vector should only be used with counters, and it calculates how much the value increased by in the. So going over here, let's choose HTTP request total metric on the path slash. Why not? What I'm going to do is make 10 requests to it now. So I'm going to send a lot of data. Maybe not 10, we'll see how much. And then what I'm going to do is say HTTP request total in the past 3 minutes. Specifically for the path slash, just to keep things intuitive. Okay, so the increase in requests within the 3-minute window at this timestamp is 66, and then now it's 77. So 77 minus 66 is 11. So if I calculate the increase in requests within the 3-minute window, am I going to get exactly 11? We'll find out. And we get 11.999. And the reason that we don't get exactly 11 is because it assumes that, hey, maybe this window isn't very big and it only caught part of the increase. So it tries to extrapolate to a fuller time range, which is why we don't get exactly 11. But the more you increase the window, the less that it has to extrapolate, and the smaller this value is going to get. The closer it's going to get to the increase that it originally calculated. Okay, so now we get 11.73. And that is how you can measure the total number of something and how it increased over time. Okay, now there are many functions. You really got to be careful to choose the ones that apply to counters and choose the ones that apply to gauges. So while increase measures how a counter value increases over time, the delta function is used to measure how a gauge value changes over time. And you really got to be careful to apply your functions on the correct metrics. Really look at the documentation. All right, and now let's look at how we can manipulate the existing labels of a metric. The first function we're going to look at is label replace. And what this does is it simply creates new labels from existing ones using regex patterns. And this is very useful, for example, if let's say you're making PromQL queries from Grafana and you want your panel to have an insightful label that doesn't already exist inside the metric, among many other use cases. So the metric we'll start by looking at is HTTP request total. Okay, it's got all these labels: instance, job, method, path, and status. And I just want to give it a new label called new label. Who cares for now, just for the sake of example. Label replace. So the first argument is the metric itself. The second argument is the new label, which I'm going to call new label to keep things intuitive. And the third argument is the replacement value, what to put in the new label. You could just put a standard string like hello world, but that wouldn't be very interesting. We want to put in what is commonly known as the first capturing group. I'll explain what that is in a second, but it essentially connects to the fifth argument, which we'll define in just a sec. The fourth argument is the label that we want to extract our value from, the source label. And the fifth argument is the matching pattern. So parentheses in regex, they define the capturing group, what's being captured. In this case, anything that comes after the slash, so it can match any single character that comes after the slash, and asterisks means there can be 0 or more characters after the slash, but essentially, anything that comes after the slash, we want it to replace this $1 as the value for our new label. Okay, so it follows that each metric is now going to have a new label that equals whatever comes after the slash. All right, pretty cool stuff. All right, and that's pretty much all I want to cover for label replace. It creates new labels from existing ones using regex patterns. Another function that we can use is label join, which combines multiple label values into one new label. And this is useful when you want to create combined labels for better grouping and filtering. So we'll go ahead and say label join. The first argument is the metric itself. I want to create a new label called instance info that combines the values of two other labels. In the third argument, we specify the character by which we're going to separate these two values. And in the fourth argument, I specify the value of the first label, followed by the value of the second label. So what this is ultimately going to produce is the value fast API app, fast API app 8000 for instance info. Okay. This chapter is going to be very simple because I just want to touch on monitoring resource usage. So a metric you'll encounter very often is process CPU usage. This one just shows the current CPU usage percentage. In this case, 4.9%. Why is it inconsistent? Let me refresh. Oh, it's just a matter of Prometheus scraping the data at the right time. And another one you'll often encounter is process memory usage bytes. This is in bytes, but what I can do to convert it to megabytes is divide by 1024. That gives us kilobytes. Divide by 1024 again, and that gives us megabytes. Chapter 13 will be focused on visualizing data trends. For instance, what if I want to show the rate of change of memory usage in the past hour? If we look at the documentation, the rate function is used to calculate rates of increase for counters. But memory usage in this case is a gauge metric, and the equivalent of rate for gauge metrics is known as deriv. All right? This calculates the per second derivative and should only be used with gauges. And we're about to use it with a gauge metric called process resident memory bytes. So let's go ahead and do that right now. We'll just apply deriv, process resident memory bytes. Oh, we don't need the value itself. And process resident memory bytes, this means the memory actually used by the process in bytes. And we want to visualize the rate of change over some time span. I'm going to make that into an hour. Actually, before I show you the final output, what I want to do is just show you the metric itself in the past 5 minutes, if you will. Here we get a range vector with two time series, one for the fast API app, the application whose metrics Prometheus is scraping, and one from Prometheus itself. Prometheus also keeps a metric for itself that keeps track of the amount of memory that it's using. And here we barely see a change for my Python app because fast API apps, they typically have very stable memory, but Prometheus, it naturally grows as it collects more data. So we can expect a higher rate of change for that, and a 0 rate of change for my fast API app. Let me just stop talking and apply the function. Let's say over the last hour. So my fast API app is essentially growing at 0 bytes per second, and my Prometheus instance at 2 kilobytes per second for short. And now in this final chapter, we're going to explore some advanced functions. Although they're labeled as advanced functions, I find them to be very, very intuitive. So let's assume we have the metric HTTP request total, and I want to retrieve the top 5 time series with the highest number of requests. So what I can do is say top K, get the top 5. So the first argument is how many results you want to display on which instant vector. We get 4, 20, 22, 94, 21, 6, and 5. The rate function also produces an instant vector of, in this case, requests per second for each time series. And I can rank them by the highest requests per second to lowest. All right, simple as that. We just recently made requests here. That's why we're seeing actual values for it. Metrics requests are always being made there. Here we haven't touched those in a while. And just like there's top K, there's also bottom K, but then this one gets the bottom 5 values, which have the lowest request rates in this case. So you're just going to get 0 all around. And that's pretty much it for this PromQL guide. This tutorial covers almost every major topic, so if there were some topics that you weren't sure about, go back, take some notes. Trust me, I wish I had a tutorial like this when I was getting started, because the Prometheus documentation is very interesting to say the least. In future videos, we're going to perform PromQL queries in order to construct Grafana visualizations, so make sure to tune in for that. And finally, if you haven't signed up for my Kubernetes course yet, what are you doing? Link is inside the description. I'll see you in there. Perfect. Now that we understand PromQL, let's put it to work by creating powerful Grafana dashboards in Module 3. I'm going to play the video now. Enjoy. In this tutorial, you will master the process of transforming raw metric data into a Grafana dashboard with insightful visualizations. I will provide you with a pre-configured environment so that we can focus entirely on building each dashboard panel step by step. This tutorial is divided into many chapters. In Chapter 1, we're going to start by discussing the 2 methodologies that will guide the creation of our dashboard, which are the read and use methodologies. The read methodology focuses on metrics that affect user experience. The use methodology focuses on system-level metrics. And so by creating a dashboard that combines the read and use methodologies, we can ensure comprehensive monitoring of both user experience and system performance. Okay? And now before starting, make sure you have the same environment. All right, let's begin. If you followed the tutorial correctly, then you should have one Python web application that is exposing metrics at a particular endpoint. You should have an instance of Prometheus that is constantly scraping the data at this endpoint and saving the metric data into its Prometheus database. We can confirm that all of this data is being saved into Prometheus by grabbing one of the metrics and trying to query for it through the Prometheus UI. The Prometheus database gives us back results confirming that all this data is indeed being saved into Prometheus. And based on your setup, you should also have a Grafana instance that is connected to the Prometheus data source and is therefore able to query the same metric data and be able to monitor the performance of our application. Okay, because all the PromQL queries we're going to make in the Prometheus UI, we need to be able to make in our instance of Grafana, because these PromQL queries are going to be used to construct the panels in our dashboard. The dashboard we're going to create is going to be called Web Application Monitoring Dashboard. The reason I'm calling it this is because it's going to show you the best practices needed to monitor any type of web app, whether that's a Spring Boot app, a Flask app, a Node app. We're going to use the read and use methodologies to extract the most valuable insights from our metrics and be able to really get a clear sense of what's happening with our app. All right, so before we get ahead of ourselves, one metric that is common to any type of application is when the application, excuse me, when the application started up, okay? In this case, the metric that our Fast API Python app is exposing is called process start time seconds. And what this basically expresses, it is the specific point in time, the specific point in history when our application was started up, expressed as a timestamp in seconds. So what I can do is, first of all, ensure that this is being saved into Prometheus. It indeed is. But Prometheus shows us an instant vector of two values, one for the Fast API app, one for the Prometheus job itself. I'm only interested in the Fast API app, so I'll apply a label filter. Okay, so what I can do here is take the current time now, expressed as a timestamp in seconds, and subtract the time at which this application was started up. And what that's ultimately going to give me is how long the application has been up for. In this case, 1300 seconds, which makes sense because I've had the application up for quite a while. And so now I can use this query to display that same value inside of Grafana. So I can go ahead and create, excuse me, gonna grab some more water. Where was I? Yeah, I'm gonna use this query to display that same value inside of Grafana. So the panel I'm gonna create is a stat. Stats are very effective for for displaying single values that serve as quick indicators. So this one is going to quickly indicate the process uptime using the following query. So here you see three tabs: explain, builder, beta, and code. Make sure you have code selected so that you can paste in your PromQL query. And we see that our app has been up for 1300 seconds. Yours is probably going to be different. Okay. And we see that the value is displayed in red because by default, there's a threshold that's been applied whereby if the calculated value is bigger than 80, it's supposed to turn red. So if I made this like 1600, it would turn into the base color. It doesn't really make sense to have a threshold for process uptime because the longer your process is up for, the better that is, right? So we can keep that as a single green color. You can remove the graph showing behind the value. We don't really need that. And the background, we'll just give it a background of green. And now this value is in seconds, right? We have a timestamp representing the current time in seconds minus a timestamp in the past that's expressed in seconds. The result of that is going to be a value in seconds. So you want to make sure that you tell Grafana the unit. Why? I'll tell you in just a second. In just a second, no pun intended. By telling Grafana that this is a value in seconds, it knows that expressing a value of 1000 seconds isn't very practical. So it knows to convert it to minutes, okay? And if you have too many minutes, Grafana is going to know to convert that to hours, all right? So we can go ahead and apply that, and we have a panel that shows us the process uptime. Very, very cool stuff. I'm going to make this a little bit smaller to make room for the other quick indicators that we're going to add. All right, that's good enough. Now, before I actually add any more panels, I want to make note of the fact that we don't want to hard code values into our labels, because what if these values end up changing in the future? What if the value for the job label ends up being Python Fast API app as opposed to Fast API app? You don't want to change every single PromQL query in your whole dashboard. That's just going to be a maintenance nightmare. So you want to replace this with a more dynamic variable. The way to do this is to go back to the settings, create a new variable, okay? This variable will will display many values based on a query that is made to the Prometheus data source. Grafana has a built in a function called label values. What that's going to do is scan the data source to check for every possible value for a label of your choosing. So if I choose the label job, what this does is it scans every single metric that has the job label, and it displays all the possible values that it found for that label. Okay. In this case, here we have all these metrics being saved into Prometheus. The generation label seems pretty unique to just these two metrics, so I should only expect three possible values for it, 0, 1, and 2. So if I try to scan all possible values for the generation label, I should get exactly that, 0, 1, and 2, but that's not the one I'm interested in. Okay, I want the job label to allow the Grafana viewer to be able to select between the Fast API app, the Prometheus app, and if he wants to select both, we can include an all option. Okay, we'll update that label. Excuse me. I have a pretty bad cough. Save the dashboard. All right, and now instead of setting this equal to the hard-coded Fast API app, we can set it equal to the job. Nothing changes, which is the intended effect. All right. In accordance with the RED methodology, the next thing we want to display is a quick indicator that shows how many requests are happening within a particular time frame. Too many requests might slow the application down. And so that's something that might affect performance. So we need to plot it. Okay. Now, if you look over here, you'll see 13 requests have been made to the path / by me before recording this video. 118 requests have been made to the path / metrics. Some partly by me, most of them by Prometheus itself because it's constantly scraping all the metric data at this endpoint. What I want to do is I need fresh data in the past 5 minutes. So let me go ahead. Excuse me. Is make 3 requests at the root path. Maybe let's say 1, 2, 3. Why not? We'll say 4. Now you can see it's been updated to 18. And now I can grab this metric, query it over here. I get an instant vector with 2 values, one that shows 18 requests for the path / 120 for the path / metrics. What I want to do is measure the increase in these requests in the past 5 minutes. So this estimates how much the value increases for each time series within this time range. In the past 5 minutes, it estimates an increase of 5 requests for this time series, 23 requests for this one. And now what I want to do is get a single value for all requests being made to my app, being made for the job Fast API app. And you know what? Just for the sake of it, let me apply this filter. It shouldn't make a difference because both of them have this job label in common. And then I want to aggregate this instant vector of values into a single sum. Okay. And this displays the total increase in requests for the Fast API app in the past 5 minutes. What I can do is copy this into Grafana in order to display that same value as a quick indicator to show the rate of request increase. So total requests within some time span. Okay, so here I get 28.4 requests. And regardless of how I change this range, it doesn't really make a difference. We still get 28.4. What I want to do is have the quick indicator be computed based on what the range is. In this case, 15 minutes. 5 minutes, we get back 28.4, 15 minutes. Okay, beautiful. Because that just makes more sense, okay? And we want to reference the job, not a hard-coded string. And we don't need a graph that shows us how this computation would change over time. Remember that Prometheus is a time series database, and Grafana is able to apply this computation over different time intervals. We're just grabbing the latest value, in this case, 15 minutes, which would be 69.1. We just want the latest value. We don't care about the graph itself. Remove it, add a background. We don't want a threshold for this. Doesn't really make sense to have one. Having 0.1 of a request doesn't really make sense. So let's have it round to 0 decimals. Okay, apply this. Sweet. All right, now the next quick indicator that I want to display is the error rate in accordance with red RE. And the error rate, in order to have data for it, what I want you to do is to download Postman. Okay, pretty easy to download. Once you do that, if you followed my other tutorial correctly, then you should have a collection.json file that contains a collection of requests that can be made to the app. So once you have Postman set up, what you want to do is to your workspaces, create a new workspace. Let's create a blank workspace, click next, call the workspace something. You know what? I'll just do it with you. Rayan tutorial 1. And then into that workspace, import the collection.json file. All right. So where is Postman? So annoying. We'll go ahead and import our collection into Postman. And this here gives me a convenient collection of requests that I can make to my app. So we'll start by making a bunch of GET requests. I want to make a bunch of successful requests first, followed by some POST requests. All right, created a 4th item, a 5th item, a 6th item. We'll just keep grabbing the first item just to give our metrics some fresh data, okay? And now what I want to do is I'm going to delete the first item, okay? And then I'm going to try deleting it again, and I'm going to get a 404, okay? So because now I'm getting 400 errors, the application is going to report that as a metric, which will eventually be saved into Prometheus, giving us data for errors as well. All right, let me do that a few more times. I'm going to try updating an item that doesn't exist. That should give me some 400 errors as well. So I'm just simulating a bunch of errors in order to get some data. Nothing special. All right, and now, given that we now have the data, we're ready to make the queries. Okay, so I'll go ahead to my metrics. We'll see that now the application is reporting many requests. Some are unsuccessful with a failed status, showing me how many of them failed at which path and how many of them succeeded at whatever path, okay? So I can go ahead and just run increase in HTTP request total over the past 15 minutes. And I want to filter the results to just show me, for now, the increase in requests for anything that has a status that starts with 4. Not exactly equals 404, has a status that starts with 4. And the way to do that, as you learned in my PromQL tutorial, is to use regex matching. So I'm going to filter by setting a status equal to a regex pattern, where it starts with the literal number 4, and what comes after could be anything else. This is to also account for errors that could be 401, 403, 499, whatever, okay? And in this case, it should essentially grab all the 400 400 errors. In this case, we just have 404 errors. And this gives us an instant vector of 2 values, which we want to sum into a single value. Okay. So now we have the total increase of 400 errors in the past 15 minutes, and we can divide that by the total increase in all the requests, regardless of whether they succeeded or failed. And that should give us a percentage. And the amount of failed requests versus successful requests, which in this case is 6%. My recording shut down out of nowhere, so I'm re-executing this 5 minutes later. It's now at 7%. Okay, whatever. So 7% of requests are erroneous. Now, what I want to also factor in for is server-side errors. So any 400 error is a client-side error where it's the client who made the mistake. In this case, trying to update an item that doesn't exist. A server-side error is one where the error happens on the server and it's represented by 500 status codes. So what I can do is take the sum of 400 status codes and add that to the sum of 500 status codes, okay? Wrap those up into brackets and get the sum of both those values before dividing it by the total number of requests, regardless of the status code. We get an empty query result. Why? Let me just copy this. Let me just copy this somewhere safe. We'll come back to it. And so now let's just query the total number of requests, regardless of status code. And there are no 500 status codes. Okay, so if you try to include this in your query, we're going to get no results. And the problem with this is it kind of messes up everything else, right? So what we want to do is set it up such that if there are no 500 errors, then what we want to do is say or vector 0. Just give back a value of 0. And that way it doesn't, screw everything up. So we'll go ahead, copy this back over. Let's get the total increase in 400 errors. If there isn't an increase, then what we want to do is say or vector 0. Okay? Same thing over here. If there are no results for 500 errors, we can say, oh, not over here, or vector 0. And then in this case, this is going to be 0. This is going to have a value, so this won't really affect anything. We're still dividing the total increase in requests that experienced errors divided by the total increase in requests in general. And now we get 0 because the 15-minute time window now isn't enough because I was actually gone for quite a while. Let's make this 20 minutes. Beautiful. 5% errors in the past 20 minutes. Let me go ahead and redefine this query over here in order to display it as a stat in Grafana. All right, but instead of 20 minutes, we want to specify a dynamic range. Yep, over here as well. Over here as well. Instead of fast API app, let's use the job variable, which in turn has fast API app selected. And we want to view it over the past 30 minutes. All right, we got a 3% error rate in the past 30 minutes. Not bad. For the threshold, we'll say anything above 0.1, 10% errors, that's when we want to sound the alarms and paint this red. Otherwise, we'll keep it at base. And we want to specify a unit. So this is actually a percentage between 0 and 1. If we specify it as such percent, it'll convert it to a percentage, okay? And, or it will display it as a percentage, okay? And graph mode, none, background, green. Let's call this error rate. And now we just put the E in red. Excuse me, guys. This cough is so bad. All right, and now the next thing we want to plot is the duration of each request, how long each request is taking on average. The way to do that is to get the rate at which the duration of requests is increasing over time, divide that by the rate at which the total number of requests is increasing over time, and what that will give you is the average duration that each request takes. The reason why is in the explanation I'm going to put right here. Please make sure to read through it. All right. I was just too lazy to cancel units out in front of you. But anyways, if you recall from the PromQL tutorial, every histogram of request durations is followed by the total number of requests that were made on that path, followed by how long all of these requests took, the duration of those requests. So if we take the rate of this divided by the rate of that, we get the average duration that each request took on the path slash metrics, that each request took on the path slash. And if we aggregate all of that in general, we get the average duration of each request for our Fast API app. So let's go ahead and grab the duration. We're going to get the rate over the past, let's say 30 minutes. This gives us an instant vector of rates for all of the path slash items, slash metrics, etc. We want to aggregate that into a single rate. So we'll do a sum. So this essentially gives us the total duration rate. And if we divide the total request rate, what that should give us is the duration per request. On average, each request takes 17 milliseconds, okay? So we can go ahead and convert this PromQL query into an insightful visualization. I'm going to go ahead and create another stat, which will quickly indicate the average request duration, okay? Go to code, copy your PromQL query. Here, what I want to do is say for an average request duration that is bigger than 0.1 seconds. I think 0.1 seconds is a long time if that's how long all your requests are taking to process. So we'll put that as the threshold. The unit here is seconds, 17.4 milliseconds. Thank you, Grafana, for converting that. No background. We'll put a background, no graph. All right, here we have the average duration that each request takes. Make that a bit smaller. Let's expand these a little bit. All right, I think that looks a little bit better. Now the final quick indicator that I want to, let's make this smaller for the next one. The final quick indicator that I want to display is how many requests are in flight. So here we have a requests in progress metric. All of them are 0, except for the one at the path slash metrics. That's because Prometheus is always making a request to our slash metrics endpoint. So this is always going to be 1. But let's go ahead and view this over here, making sure that all these metrics are being saved in Prometheus. Indeed, they are. Now, if I sum all the requests that belong to the Fast API app, what I'm going to do, all the requests in progress, what I'm going to get is that there's one request in progress for this app. But this might be a bit misleading because it might lead me to think that one of the requests that a client is trying to make is in progress and is not happening, but that's just Prometheus trying to scrape this endpoint, right? So what I can do is restore this query to not include the path slash metrics. So path is not equal to slash metrics. So exclude the time series from our result, taking the sum of that. And there are 0 requests in progress. Beautiful. That's exactly what we want to show. Everything has been processed healthily. There's nothing for us to worry about. Add a new panel. It's going to be a stat panel. Okay. We'll display this value very quickly. 0 requests in progress. We're going to call this requests in progress. That's the R in red. All right. We'll do the usual. Excuse me. No graph. No background. We'll say if there are more than 10 requests in progress, then we want to sound the alarms. And no need to put a range for that one, I don't think. That's it. Let's just make this a little bit smaller so that it fits on top. Beautiful. And that's it for the quick indicators. When someone quickly looks at this dashboard, they're going to see that the application is relatively healthy. It's been up for a while. Not that many requests have been made. The error rate is relatively low. Each request is taking on average 17 milliseconds to process. No requests in progress. Everything is good. But now we need some panels that will allow us to gain a deeper understanding of what's going on, and we'll do that right now. So let's go ahead and create some rows. Oh, what am I doing? Create a new row. The first row I'm going to call requests. And the second row I'm going to call errors. I'll fix this up in just a second. The third row I'm going to call duration. Fourth row, system metrics. These I can move on top. They won't belong to any particular row. Requests is going to go on top. So you want to collapse the row if you want to move it. And then to its right, you'll see something that you can use to drag your row. Drag your errors second, not first. Drag duration third. All right. So for the requests row, starting with API throughput, what you want to measure is the requests per second for every single path. Okay, so we can go ahead and reflood our application with a bunch of requests. So I'll send a bunch of requests for the root path, maybe like 6 or 7 requests. We'll create some more items. Keeps creating more items. Cool. All of them seem to have an item ID of 6. Why not? We'll retrieve. Item not found. Oh. Remember, the item had an ID of 6, so we'll use that. Okay. We'll keep sending requests there. And now we should see that the application reported a batch of brand new metrics right over here. Okay, I do see the update. Let's go ahead and perform a query for HTTP request total. We see the same values reflected over here. And now what I want to do actually is measure the rate of requests. for the job Fast API app over the past 5 minutes. So rate, what it is it measures the amount of requests per second, essentially the API throughput. So 0.02 requests per second were made on the path slash 0.018 requests per second were made on the path slash item slash 6, a GET request. 0.05 requests per second were made on the path slash items for the method post, so on and so forth. This is nothing new. We covered rate in a lot of detail in the PromQL tutorial. But let's go ahead and use this query to construct a new panel. So this panel is going to be called API throughput. And that's pretty much it. It's going to be a time series panel. Choose code, paste in the query from before, and let's have it fill. All right, so this shows us that there have been 0.067 requests per second for the path slash metrics. Let's view the last 5 minutes. 0.0526 for the post method slash items, so on and so forth. But now these legends are very verbose. Okay, well, it follows that the options is set to verbose. We don't want to show every single label for each time series. We want to have a custom legend where we specify just the labels we want to show in between two brackets. I'm just going to show the method for each time series, followed by the path. Excuse me. Followed by the status. Actually, no need for the extra spacing. This looks a lot better. And now what I want to do is include units. So if I go down, the unit is requests per second, throughput. Beautiful. You can go ahead over here and modify the graph style. I'll leave the line width as it is. You may feel free to adjust the color scheme. I'm satisfied with what we have at the moment. So that's API throughput. We'll put that under the requests row, and we'll drag that, make it a lot bigger. And now the next thing I want to monitor under the requests row is the requests by status code. So over here, what I'm going to do is I'm going to apply a sum. Okay. But what I'm going to do is I'm going to aggregate the values based on the status code. So in the end, there are only 2 status codes. You know what? Let me create some more data. Let me create a lot of successful requests on the root path. 2, 3, 4, 5, 6, and 7, 8. Let me delete items that don't exist, creating some 404s. All right. No, that's not what I wanted. Okay, giving Prometheus the chance to pick up the 404s. It did. All right, now what I want to do is aggregate by the status. So essentially what we're going to have is 2 values aggregated for all time series that have the status 200 and aggregated for all the time series that have the status 404. If there was a larger variation of statuses, we would have seen more values. In this case, we're going to see an instant vector of 2 values. Okay, and now what we can do is put both of these values in a pie chart that clearly displays how much more of successful requests versus unsuccessful requests there are. All right, so I can go ahead and create a new panel that is a pie chart. Okay, I'm going to call the panel requests by status code, and the pie chart will be based on these two values right over here. And here we actually see that there were many more 200 requests as opposed to 400 requests. And this legend is a bit ugly, so let's customize it to just show the static string status followed by the label itself, status. Beautiful. And now instead of the following pie, let's use a donut instead. Because who doesn't like a nice donut? Much better. All right, we'll put that under requests. Let me make it a bit bigger. All right, looking good so far. Actually, what am I doing? This should go under errors. We already have the API throughput showing us the requests per second at every single path per method. We have the requests by status code, how many of them are errors, how many of them are of status 200. If for whatever reason we had 500s in there, those would show in the pie chart as well. Now we want panels that show the duration. Okay. Now looking at all this metric data, here we see a bunch of histograms, okay? If you did my PromQL tutorial, you know exactly what a histogram metric is, but in case you didn't and you're too stubborn, you don't want to watch my tutorial first, I'll briefly summarize what they are. So here at the path slash, there are 26 requests in the bucket 0.005. So 26 requests took less than 5 milliseconds. The buckets are cumulative, so one more request took less than 10 milliseconds, 5 more requests took less than 25 milliseconds, so on and so forth. So this histogram distribution essentially tells us how long requests took in general, okay? But now, what if we want to, from this data, be able to extrapolate how long did 95% of the requests take? How long did 50% of the requests take? That's where the histogram quantile function comes in, which we covered in much great detail in the PromQL tutorial. So if we go ahead and just paste this into PromQL, without applying any filters, it shows us every single histogram for every possible type of request. And for each bucket, it shows how many requests took less than 0.005 seconds for some path, some method, etc. What we want to do is calculate the rate at which the value in each bucket is increasing. So we'll calculate a rate over 5 minutes. Just for the sake of it, we'll add the job label. All right. Okay. And this is much clearer. Here we see at the path slash metrics, this bucket gets 0.06 requests per second. This bucket gets 0.02 requests per second, so on and so forth. All right. And now what we can do is perform a sum by less than or equal to label. And so in total, the 10 millisecond bucket gets 0.02 requests per second. The 25 millisecond bucket gets 0.05 requests per second. And now this, what I can do is feed it into my histogram quantile function. How long did 95% of my requests take based on this histogram data that I'm feeding it? 95% of my requests took 0.026 seconds. Let's see how many 50% of my requests took. 0.009 seconds. Now, regardless of whether I use rate, increase, or whatever, it doesn't matter. Even if I remove increase and remove the 5 minutes and just do a sum by LE, it'll work out to be the same value as well. Why is that? Because as you might have picked up from my last tutorial, histogram quantile works on proportions. So it looks at the proportion, in this case, of rates per second in the 5 millisecond bucket, the 10 millisecond bucket. And based on what those proportions are, it will estimate how long 50% of requests took, 90% of requests took. So it doesn't really matter what function you apply here, whether that's rate, increase, or whatever. Histogram quantile just cares about the proportion of the values per bucket. Okay, so we can go ahead and apply this in our Grafana dashboard. We'll create a new panel. And this panel is going to be called API Latency Percentiles. This is going to have 4 PromQL queries. The first PromQL query is going to measure how long 50% of requests took. For our fast API app, remember to use the variable job. I wonder if we did this before. Anyways, whatever, doesn't matter. We're going to perform this measurement in 5-minute intervals. We can go down here to B. How long did 90% of requests take? Go down to C. How long did 95% of requests take? How long did 99% of requests take? Okay, we can give this a legend of P50. Oh, no, this doesn't need to be wrapped in brackets. It's a static value. We can give this a value of P90. P95. P99. All right. API latency percentiles. Beautiful. This gives us a pretty good indication, come on, of how long requests are taking to process. So 99% of requests are taking 0.04 seconds to process. 50% of requests are taking 0.01 seconds to process. Not bad at all, if you ask me. Let's go ahead and use the unit seconds. All right. Just so that it adjusts our graph and looks pretty good. Now, another panel we can use to measure duration is the average duration of request, which is something that we, actually, before we move on, I want to make sure I didn't hard code the fast API app string. Indeed I did. Let me go ahead and fix that over here. Fix that over here as well. And now, average request duration is something we already plotted, but now instead of doing it to display one single value, we're going to be displaying it across a time series. Instead of 30 minutes, what I want to do is grab it in 1-minute intervals. Grab the average request duration in 1-minute intervals and be able to view it across whatever range that we choose. Okay? And for the legend here, we're going to say show the method, show the path, and show the status. No need to say sum. We can just say rate divided by rate. All right, beautiful. I'm going to call this panel average duration of request. No need for a threshold. I think this looks pretty good. Put that down for duration. For some reason, we see no data for API latency percentiles. I wonder what's going on there. Oh, it was just a little bit of a glitch. Okay. So here, once again, we're measuring things in 5-minute intervals, but we're able to filter across much longer time ranges. Cool. And now we can go ahead and plot system metrics. So in accordance with the use methodology, and we'll start by plotting resource utilization. Okay, so we can go ahead and create a panel to display CPU usage. I'm going to call it CPU usage. And we want to measure the CPU usage. This is a percentage, by the way, for our fast API app. So we'll say process CPU usage job is equal to fast API app. We can go ahead and paste this right over here. We don't want to display a time series. We want to display a stat. All right. No need for a graph. We want to not hard code fast API app. We want to put job. And this is a percentage. So we can go ahead and say percent between 0 to 100. All right. And we can drag the CPU usage panel over to system metrics. So one important metric to monitor, which most applications expose, is how many open connections the application currently has to different files, sockets, and types. So we want to paste that over here. And there's usually another metric that complements it called process max, which is the maximum amount of connections it's allowed to have. So we want to divide this by the maximum amount of connections it's allowed to have. And that gives us a percentage that we can display. All right. 0.0008 is a very, very good percentage, which means we haven't come close to reaching the max. So we can go ahead and display that as a stat. Remove the threshold. Where's the unit? This is a percentage between 0 to 1. Call this open file descriptors. Maybe you could add a threshold to stat once it reaches a certain percentage, but we're not even close at this point. So I'm not too worried. We'll put no graph, put a background. Open file descriptors, that's going to go along with CPU usage. Another piece of resource utilization that we can plot is memory usage. So if you go back to metrics being exposed by the application, almost any app will expose these metrics: process, resident memory bytes. This is the actual physical memory, the actual RAM being used by the process. And we can plot it as follows. Let's go ahead and we'll apply the filter. We just want to view it for the fast API app. This metric also applies to Prometheus as well. It's just how common it is. So we'll go ahead and plot that. Create a new panel. For job. Okay. Add another query. Something else you typically want to plot is the process virtual memory bytes. This is the total amount of virtual memory space that's allocated to the process. So this includes both RAM and swap space. So we do job is equal to fast API app. Beautiful. Let's go ahead and put that into our graph so that it can be monitored from a Grafana dashboard. All right, we have that going as well. Something else you want to typically monitor is the memory usage in bytes. All right, that kind of explains itself. So this is the, just for the sake of explaining anyways, it's the total memory that's in use by the process. Overall memory consumption, if you will. All right, we can go ahead, paste that into here as well. Now we're monitoring memory. And what we do is call this panel memory usage. In the legend, excuse me, we'll just call this resident memory. We'll call this virtual memory. This memory usage. Cool. You can grab that. Let's view in the past 15 minutes. Put that here on the right. And now we want to monitor our applications' garbage collection activity. And we can do this through the metric Python garbage collected object collected total. We can go ahead and plot or just kind of get the values for the job fast API app. All right. And we want to get the rate at which objects are being collected per second over the last 5 minutes. This is a very crucial metric to monitor for all generations, generation 0, generation 1, generation 2. So for generation 0, this should have the highest rate to indicate frequent but very quick collections of newer objects. Generation 1 should have a moderate collection rate, assuming that most objects are garbage collected in this generation. So given this trend, we can see that our application is fairly healthy. Now, while teaching this lesson, my recording randomly stopped, and in between, I have already created the following panel, which pretty much just plots what we have over here. But instead of fast API app, we'll use the familiar job label. Okay, and this essentially plots the garbage collection over 3 generations. Looks pretty healthy to me. And that's all I'm going to cover for this video. We have a very comprehensive dashboard with quick indicators to quickly tell us how the application is doing, and pretty much the same metrics being plotted here, but across an entire time series. And here we have latency percentiles that tells us how fast 99% of our requests are being processed, how fast 95% of our requests are being processed, so on and so forth. And here we have an average duration of requests plotted. We really only see data for slash metrics, but if you were to flood all of these other paths and methods with more requests, then you'd see data for those as well. And that's pretty much it. I hope you enjoyed this video. In the next one, we're pretty much gonna set all of this up, but inside of a Kubernetes environment, so I can't wait to see you in there. Now that you understand the fundamentals behind Prometheus and Grafana, we can move our stack to Kubernetes in Module 4. So we're done prototyping, which is what Docker Compose is usually for, and Kubernetes is where you'll likely be monitoring your containerized applications. I'm going to play the video now. Enjoy. In this video, we're going to use the kube-prometheus stack to install Prometheus and Grafana on Kubernetes. I'm going to show you how Prometheus is already configured to monitor the underlying Kubernetes infrastructure, and how we can configure Prometheus to monitor our own applications. So Chapter 1 covers installation, Chapter 2 covers infrastructure monitoring, Chapter 3 application monitoring. This is going to be very easy and lots of fun, so let's jump right into it. All right, so inside of your terminal, command prompt, or shell, write the command helm version to ensure that you have Helm installed on your machine. If you do get a version, perfect. If you get something to the contents of command not found, please make sure to check out the article where I show you how to install Helm on Mac or Windows. Link is inside the description. Once you ensure that you have Helm installed, we're going to use it to simplify the deployment of what's considered a very sophisticated setup, the Prometheus stack. Okay? Now, for those that aren't very familiar with Helm, I'm going to keep it simple and start by discussing what it is at a high level. So we have this concept of Helm repositories, where a repository contains many Helm charts. A Helm chart is essentially a package that combines and already contains all of the configuration files needed to set up a particular software. So to give you an example, a popular repository is Bitnami because it contains many Helm charts that simplify the deployment of very popular software like MongoDB, Redis, MySQL, PostgreSQL in such a way where they can be made very highly available within your Kubernetes cluster. Okay? Now, the Helm repository that we're interested in this particular video is the Prometheus community Helm repo because it contains all of the Prometheus related Helm charts, which one of them we're going to use to set up the Prometheus stack. All right, so here is the link to the Prometheus community Helm repo, which contains a lot of Prometheus Helm charts. We need to refer to this repo from our local Helm configuration. So here we need to say Helm repo add, and we're going to set an alias by which we can always refer to this Helm repo. You can call the alias whatever you want. I'm going to call it Prometheus Community because that makes the most sense. And we need to link this alias to the following Helm repository. Okay? And now that we've added this Helm repositories, we can actually look at all of the Helm charts inside of it. So I'm going to say Helm search repo, and I'm going to search for the Helm charts inside of this repository. And there are many Helm charts. If you scroll up somewhere, you'll find the Prometheus stack Helm chart, the one that we're going to use. Now, if for some reason you weren't able to find it, you can zero in and refine your search by saying Helm search repo. We can search within the Prometheus community Helm repo for the Prometheus stack Helm chart specifically. And there it is. We see this Helm chart where the latest chart version is 65.5.0. What if we want to search for all of the versions that are available for this Helm chart? We can say -- versions. And if there's a version in particular that you're interested in installing, you can feel free to look through all of the chart versions and make sure that they're available. In this case, I'm interested in installing the Prometheus stack version 45.7.1. So when I say installing a Helm chart, what does that mean? Let me start out by writing the command, and I'll break it down as I go. Okay, so I'm going to say Helm install. So when you install a Helm chart, you're essentially taking that package of configuration files and releasing it into your Kubernetes cluster. So every Helm chart installation is known as a Helm release. We're going to call the release Prometheus. You can call the release whatever you want, okay? And the chart that we want to install is inside of the Prometheus community Helm repository, and it's called Prometheus stack. The version of the chart whose contents we want to release onto our cluster is 45.7.1. Please use the same version of me for consistency. And now the contents of the Prometheus stack, I want it to be deployed within a particular namespace in my Kubernetes cluster. That namespace is typically called monitoring. And we need to first make sure that that namespace gets created before the Helm installation proceeds. So we can say create namespace. All right, and that should be it. And so by installing the Prometheus stack Helm chart, we're releasing 4 main components into our Kubernetes cluster: the Prometheus operator, the node exporter, kubestate metrics, and Grafana. The Prometheus operator is crucial because it automates the creation of your Prometheus instance as well as the alert manager. The Prometheus instance is essentially a time series database that's going to store all of the metric data, whether it's infrastructure related metric data or application related metric data. All of that data will reside inside of Prometheus. Okay? And it also automates the creation of the alert manager, which can create alerts based on the metric data that's inside of Prometheus. 2 other components that get deployed are the node exporter and kubestate metrics. Those essentially work together to extract infrastructure related metrics from the Kubernetes platform itself, and they're automatically set up to persist all of that data into Prometheus. So right there, we get infrastructure monitoring out of the box. Okay, and now you've got all of this metric data inside of Prometheus. How are you going to make sense of it? Well, we also got Grafana for free. Grafana is a visualization tool that can query metric data from Prometheus and based on that data, create very insightful visualizations. How do we actually make sure that we get all that and I'm not just out here lying to you? Well, we can look at all the pods that get deployed in the monitoring namespace. So here we see the Prometheus operator, which automates the creation of your Prometheus instance, as well as the alert manager. We see kubestate metrics and node exporter, and we see Grafana as well. All right, and now if you've never heard about Helm or the concept of operators before, this might have been a bit overwhelming to you, in which case I would suggest checking out our complete Kubernetes course, where we cover all of these essential Kubernetes concepts in a lot of detail. But for the sake of this tutorial, just know that through a simple Helm release, we were able to deploy the entire monitoring stack. Okay, now it's time for part 2, where we explore how the monitoring stack was already configured for infrastructure monitoring. So the gist of it is, Prometheus relies on exporters to extract metrics from particular targets. For example, a MySQL exporter would be designed to scrape metrics from MySQL. A MongoDB exporter is designed to scrape metrics from MongoDB. In this particular case, by deploying the Prometheus stack, we get 2 exporters for free. The node exporter, which is designed to scrape metrics, system-level metrics from Kubernetes nodes, like CPU, memory usage, disk utilization. And we've got the kubestate metrics, which is another Prometheus exporter. And this one is designed to collect metrics that allow us to monitor the health, configuration, and availability of all of your Kubernetes objects, your pods, deployments, and your services. And because both of these exporters are already shipped as part of the Prometheus stack solution, the Prometheus instance is automatically configured to pull all of the metrics being collected by these exporters. So it's pretty cool if you think about it. We already have Kubernetes infrastructure related metrics being saved into our Prometheus database, and we can access all of them right now. What I'm going to do is say kubectl. I want to get all of the services that were deployed as part of our Helm release. The service I'm interested in is the following because it will allow me to access a Prometheus UI that I can use to make queries against the Prometheus database. So I'm going to port forward the following service. If you don't know what the concept of port forwarding means, again, highly recommend checking out my Kubernetes course. kubectl port forward. The service is in the monitoring namespace, and the service is called Prometheus operated. And the port I want to forward is 9090, and we'll just forward it to a host machine port of 9090. So now if I go localhost 9090 right over here, I can access the Prometheus UI. Kube pod container, status running is a metric that would be collected by the kubestate metrics exporter. And this gives us information about pretty much all the pods in our cluster. A value of 1 means the pods are running. A value of 0 means whatever pod is failing for whatever reason. All our pods are good. And so it's really hard to kind of look at all of this data when it's in vector format. And that's when something like Grafana is really handy, because it allows us to create very insightful dashboards based on all of these Prometheus metrics, okay? So these queries that I'm performing right here using the Prometheus UI would also be done from inside of Grafana, except Grafana has a way of converting these queries into insightful panels where we can see how these values are changing over time. Okay, so what I'm going to do is go back over here and say kubectl port forward. This time, the service I'm interested in is the one that will allow me to open up the Prometheus Grafana UI. And I want to port forward this port 80 into port 3000 of my machine. Okay. So now if I go to localhost 3000, I can log into Grafana. So the username, the default one is admin. The default password is prom operator. Let me try it out. Now, if for some reason these credentials don't work for you, what you can do, I'm just going to stop it for now. I'll come back to it. What you can do is say kubectl get secret -n monitoring. The credentials are saved inside of a secret. Don't know what a secret is? Check out the Kubernetes course. -n monitoring Prometheus Grafana. So this gives us the secret. We want to extract its contents. So I want to output its contents. I can use the -o flag, and I want to format the output using JSON path. And the field whose value I want to get is .data, .admin password, and damn it. Let's try this again. And I can pipe the output so that I can base 64 decode it and then print out the value. Prom operator. So if you use this command, you'll be able to extract the password. All right. Let me go back and report forward. Grafana, localhost 3000, we're good. And if I go to browse, and notice how Grafana has been pre-configured with dashboards that query Prometheus. So if I navigate to this dashboard, each panel over here is actually a query that's being made against the Prometheus database to visualize the metrics that were collected by Prometheus from both system-level sources, in this case via the node exporter, or Kubernetes-specific metrics. Okay? So this dashboard over here allows us to visualize all of the Kubernetes specific metrics, the amount of running pods in all of the namespaces, the amount of running containers, so on and so forth. So it's pretty cool how we get the ability of infrastructure monitoring out of the box without having to do anything. All right, now it's on to chapter 3, where we explore application specific monitoring. So how do you monitor an application on Kubernetes? Well, first, you need to develop your application in such a way that it can expose metrics in a format that Prometheus can understand. Many applications, many web frameworks like Spring Boot, Flask, Nest, they all have dependencies, Prometheus clients, that can instrument these apps to expose Prometheus metrics. It's actually very simple. I wrote 4 separate articles that describe how various types of apps can be instrumented to expose Prometheus metrics. So like Spring Boot apps, Flask apps, Nest.js apps. If you're curious, feel free to check out the articles, links in the description below. But anyways, once you've developed your app to expose Prometheus metrics, then you deploy it in Kubernetes alongside a cluster IP service that can be used to access the application. And so now how do we configure Prometheus to find this application's endpoint where it's exposing all of these metrics and scrape this metric data every 10 or 15 seconds? This is where service monitors come into play. you'll remember that we used a Prometheus operator to automate the creation of our Prometheus instance. If you took my Kubernetes course, you'll know that an operator is a custom controller that extends the Kubernetes API and can therefore watch for custom resources that aren't native to Kubernetes. One such resource is the service monitor. Okay? And what a service monitor does in this case, it binds to your service by matching its labels. And as long as that service monitor is discoverable by Prometheus, it will configure the Prometheus instance to find your service, direct it to the application's endpoint, and scrape its metric data in regular intervals. Okay, that's enough theory. Let's put it all into practice. So here is a repository where I uploaded all of the configuration files you need to set all of this up. Link is in the description. Go to code, copy the URL that we need to clone this code. On a separate terminal, choose whatever directory you want in your local machine. Clone your code, or clone the repo, I should say, somewhere where you can easily access it. And then what we're going to do is apply every single configuration that's inside of this directory. Okay, git apply -f, apply everything in the current directory. Why am I saying git? kubectl apply -f. Okay, I already had them deployed because I was preparing for this lesson beforehand. So let me clear the output. And now let me go inside of the deployment.yaml. So this just deploys a fast API application that is serving requests on port 8000. This cluster IP service allows us to access our fast API app. So what we can do is say kubectl get services -n. Everything is being deployed in the monitoring namespace. It doesn't really matter what namespace you deploy these resources in. I just chose monitoring because that's what we had already, and I don't want to proliferate too many namespaces in my cluster. So kubectl get services -n monitoring. All right. And the service that I'm interested in is the fast API app. So I'm going to say kubectl port forward. I want to port forward the service object fast API apps as internal port 8000 to a host machine port 8000. And we need to specify that this Kubernetes object is in the monitoring namespace. Okay, so now if I go ahead and say localhost 8000, oh, spoiler alert. So this is the fast API application, and this application, I programmed it to expose metrics at the path /metrics. And if you're interested in how to instrument an application to expose Prometheus metrics, whether that's Spring Boot, Fast API, Flask, whatever, again, all the articles are in the description. But anyways, here we see different types of metrics that give us various insights about what's happening in this app. So here, one metric is the total number of requests that's being made on the empty path. So if I make a few more requests to localhost 8000 and I just refresh this, you'll see that the metrics get updated. 11 requests in total were made on the path / and 147 requests were made on the path /metrics. Anyways, because metric data is constantly being updated, we need Prometheus to regularly scrape this metric data so that it stays up to date on what's going on with this app. All right, so if I go back, here we have a service monitor, okay? This part is really crucial because it matches the labels of our fast API service. The fast API service is what allows internal access to our fast API app. So this basically configures Prometheus to find our application. And then once it finds our app, this tells it which port our app is serving requests on, the port named web on the internal port 3000. okay, you can just use the port name. And the path where the app is serving requests is /metrics. So right there, the service monitor gives Prometheus all of the information that it needs to find our app and scrape all of the app's data at the appropriate endpoint, port 8000 path /metrics. Pretty cool stuff. And this is really important as well, because if I say kubectl get the Prometheus instance inside of the namespace monitoring, and I want to output its labels in a YAML file, one important field is the service monitor selector. The Prometheus instance was installed in such a way that it can only discover service monitors that have this label, release Prometheus. So in order for the service monitor to be discovered by Prometheus, you need to make sure that you give it this label. It must match the Prometheus stack release label. And that's basically all we need. We've already gone ahead and applied all of these configurations, but in case you didn't, kubectl apply -f. All right, and now what we want to do is ensure that Prometheus is actually able to discover the service monitor and therefore scrape all of the data from our fast API app. So what we can do is remember that port forward command from before where we access the Prometheus UI. Yep, this one right over here. Let's go ahead and say localhost 9090 and access the Prometheus UI. If you go to status, targets, boom, it found our service monitor and is monitoring the fast API app at port 8000 /metrics. A state of up means that our application is healthy because Prometheus is able to find it and collect metric data from it. So by this logic, all of this metric data, let me open up, let me report forward. So by that logic, all of this metric data should be saved inside of Prometheus. Let me copy one of the metrics. So total number of requests made to the path / is 11. Are we going to see that in the Prometheus database? Let's run that same query from the Prometheus UI. Indeed, we do. So all the data is now being saved in Prometheus. How do we make sense of all this data? Well, that's where Grafana dashboards come into play. So I already created a Grafana dashboard and exported its JSON. You've already deployed it as a config map, which will automatically get discovered by Grafana by virtue of having this field, Grafana dashboard 1. So now if we go ahead and port forward the port that we need to access Grafana, we can see that we've got this fast API application dashboard. It's monitoring the request rate of our app. Let's do it in the last 5 minutes. Beautiful. And this panel could be fixed, but I'll do it in an upcoming lesson. The take-home message is each of these panels is a query that's being made against the data in the Prometheus database. So if I edit this panel, all this is a PromQL query. You can perform that exact same query in your Prometheus UI if you were to rerun it. But anyways, Grafana will get the results of this query and allow you to visualize it over time. Pretty cool stuff. And that's pretty much it. I hope you enjoyed this lesson. If you enjoy my teaching style, don't forget to check out the Kubernetes course, and I will see you in the next one. With Prometheus and Grafana now running on Kubernetes, let's understand how all the pieces fit together by exploring the Prometheus architecture in Module 5. I'm going to play the video now. Enjoy. You can deploy the entire Prometheus monitoring stack using a Helm chart called Prometheus Stack. And in this overview, we're going to break down the entire Prometheus architecture and discuss how all of these different components come together to provide a very powerful monitoring solution. It all starts with the Prometheus operator. The Prometheus operator extends the functionality of Kubernetes because it's a custom controller that watches out for custom resources, and these custom resources essentially tell it what to do. So the Prometheus custom resource in this case is also deployed because it signals the Prometheus operator to create and manage a Prometheus server within the cluster. The Prometheus server is responsible for storing all of the metric data in a time series database. The node exporter extracts system-level metrics such as CPU usage and memory consumption from every single node from every single machine in your Kubernetes cluster. KubeState metrics is another exporter, but this one collects metrics about the current status and health of Kubernetes resources like pods, deployments, and services. And both of these exporters, node exporters and KubeState metrics, they expose metrics at specific endpoints. However, for Prometheus to scrape these metrics, we need to establish a connection between these exporters and the Prometheus server. Service monitors are also custom resources that are deployed to signal the Prometheus operator to reconfigure the Prometheus server and tell it exactly where to find the endpoints it needs to scrape. And so once Prometheus knows where the targets are, it needs to interact with the Kubernetes API to gain access to these services. As Prometheus scrapes metrics from various targets, it stores this data in its internal time series database. And now Grafana is also deployed, and it connects to Prometheus and uses PromQL, Prometheus's query language, to retrieve all of these metrics and create insightful visualizations out of them. And so this setup allows us to monitor both system-level metrics collected by the node exporter and Kubernetes-related metrics collected by the KubeState metrics exporter, and allow us to visualize them in very nice and insightful Grafana dashboards. And we get all of that for free by simply deploying the monitoring stack using the Helm chart kube-Prometheus stack. However, we want to go even further now. We don't want to limit ourselves to just monitoring system-level metrics, as important and essential as that is. We want to also monitor our own applications. So now we can go ahead and deploy our own application. It could be a Flask application if you want. And now you need to instrument that application to expose metrics at a particular path. Then deploy your own service monitor that signals the Prometheus operator to reconfigure Prometheus to discover your applications as metrics endpoint and collect your applications as metrics. In Grafana, you can now create dashboards that visualize these application-specific metrics and monitor your application's performance in real time, similar to how we were monitoring the system-level metrics. And now finally, collecting and visualizing metrics is essential, but being proactively notified about issues is just as critical. That's why we have the Alert Manager custom resources that signal the Prometheus operator to manage the creation of an Alert Manager instance. The Prometheus Rule custom resource sets conditions for alerts that should be fired, such as when CPU usage reaches a certain level. And so Prometheus receives all of these rules that are defined via the operator, and when it detects that a certain threshold has been reached, it notifies Alert Manager, which sends alerts to the right channels like email, Slack, or PagerDuty based on predefined settings. And that's it. I hope you enjoyed this Prometheus overview. If you enjoy my teaching style, make sure to check out our Kubernetes course, and I will see you in the next one. Now that we understand the architecture, let's start monitoring applications that require exporters. So unlike our web app that directly exposed its own metrics, databases and third-party software like MySQL, they need special exporters to expose their metrics to Prometheus. Let's begin with MySQL in Module 6. I'm going to play the video now. In this video, you will deploy a minimalistic instance of MySQL alongside a Prometheus exporter, which will extract metrics from MySQL. Then we're going to configure Prometheus to grab these metrics and save them in its time series database so that we can finally access these metrics from Grafana and visualize them in a Grafana dashboard. This video is composed of 5 chapters, and before we dive into any of them, I need to list the prerequisites needed to continue with this video. Number 1, you should have Helm installed and set up on your machine. If not, please check out this article, or this one, wherever I need to point to, and then come back. Link is inside the video description. Number 2, you should have Prometheus and Grafana installed in your Kubernetes cluster. If not, please check out this video, or this one, wherever I need to point to, and then come back. Link for that is inside the description as well. And that's all. We can start with chapter 1. All right, let's party. So I already have all of the resources that we're going to need for this lesson set up inside of a repo called MySQL Prometheus sample. I left you a link to this repo inside of your video description, so make sure that you go to it, grab the link that we need to clone this repository in some directory within our computer. I'm going to clone it directly into my desktop directory where it will be very easy to access. So I'm going to git clone it there. Let me increase the size so that you can see. Alrighty. Now, you can't really see it because I have a few screens. So let me drag it and I'm going to launch this inside of VS Code. Use whatever editor you want. Doesn't really matter. And I'm going to create a new terminal window. Now, if you searched for this video, then you probably already have MySQL set up in Kubernetes. In this case, no need to do this step. If you were following along in the Prometheus playlist, then we're just going to deploy a very minimalistic instance of MySQL. We're not going to deploy anything crazy just because the focus is on setting up a MySQL exporter to monitor a MySQL database, so it doesn't need to be anything crazy. Normally, I'd recommend using a Helm chart or an operator to deploy enterprise software like MySQL, MongoDB, etc. But in this case, we're happy just deploying a simple secret, service, and stateful set to have a minimalistic setup. All of these are going to be deployed inside of a namespace called database monitoring, so we need to start by creating that namespace. kubectl create namespace database monitoring. All right, so here we have the namespace created. Now we're going to kubectl apply -f all of the resources inside of the MySQL folder. And that's pretty much it. We have a stateful set where all our MySQL data is going to be persisted in a persistent volume. We have a service that can be used to access the MySQL pod. We have a secret that will be used to authenticate against MySQL and be able to make queries to it, make API calls to it, etc. So if we say kubectl get pods -n database monitoring, we should see a MySQL pod. Now, alongside this MySQL instance, I want to deploy a MySQL exporter that will consistently make API calls to it and try to extract metrics out of it, okay? That's what a Prometheus exporter is for. Prometheus exporters, whether they're for MongoDB, PostgreSQL, Redis, which I will make videos about in this playlist, what they do is they consistently make API calls to a target database and try to extract Prometheus metrics out of it and expose them at a particular endpoint. All right, just give me 1 second to drink some water. We can look at the Prometheus community Helm repository that contains all of these Helm charts. Okay, so what I want you to do is go to the video description and grab this link. Once you grab it, we need to add this Helm repository into our local Helm configuration. So I can go ahead here and I'm going to say Helm repo add. You can give the repository an alias within your local Helm configuration. I'm just going to call it Prometheus Community. You can call it your dog's name, your cat's name, doesn't really matter. But this is more intuitive. I already had the repository, so it gives me this error, in which case, just to make sure, I'm going to go ahead and update the repo. Helm repo update, Prometheus Community. All right, and now we need to make sure that the Prometheus Community Helm repository contains the MySQL Helm chart. We can do that by searching the Prometheus Community repository, Helm repo search. We can use this alias to search the repository we just downloaded. Oh, I'm such a doofus. The actual command is helm search repo. I always confuse this. All right. And here you'll see that the Prometheus community allows us to deploy many types of exporters using Helm. The one we're interested in this video is, it's in alphabetical order, Prometheus MySQL exporter, okay? Before we go ahead and install this exporter, we need to configure the values that will steer that installation. So if you took my Kubernetes course, which I highly recommend you do if you haven't, link is in the description. If you took my Kubernetes course, you'll know that a Helm chart simplifies the deployment of very complicated software, whether that's MySQL, whether that's Redis, Mongo, etc. Because what it does is it combines, it packages up all of the Kubernetes objects and manifests inside of a templates folder, abstracts it away from you so that you don't have to deal with it, and it gives you access to a values file whose values you can configure to steer the deployment towards one that suits your purposes. So really, whenever you're using Helm to install a software, it comes down to being a puzzle, a very fun puzzle where you just got to look at what the default values are and knowing which ones you need to change. So before we even think about installing this Helm chart, what we need to do is look at what all the default values are and adjust them accordingly. So what we can do is go over to GitHub, where we can see the source code for all the Helm charts, okay? I'll leave you this link inside the video description. Go to the Prometheus community charts. We'll scroll until we see the Helm chart for the MySQL exporter. All right. Inside the templates folder, we have a bunch of different Kubernetes objects that we don't have to worry about ourselves. The only thing that we need to modify is the default values inside of the values.yaml file. All right. The image, obviously, we don't need to touch. The service provides access to our MySQL exporter at a particular port. That's fine. Service monitor is something we're going to have to modify because you'll remember if you were following along with this playlist that a service monitor is what configures Prometheus to discover your metrics endpoint. All right, so right there, this tells us that the templates folder contains a service monitor object, and we can use these values to steer the logic for that service monitor's deployment. So here we can control whether or not that service monitor is enabled, which namespace it's deployed in, etc. And if we keep scrolling down, this is really interesting to me. All right, this is the first thing you should ever modify when changing one of these Helm charts, and that is the connection parameters. So the host is what's going to allow our exporter to find our instance of MySQL. And once we configure the host, we need to tell the exporter which port our MySQL instance is serving requests on. This seems to already be correct, but we're going to override it within our own values file anyway. The user is what the exporter is the username the exporter is going to use to authenticate against our MySQL instance. And then here, it allows us to extract a password from a secret that MySQL exporter can use alongside the username to fully authenticate against MySQL and therefore be able to connect to it. All right. Before I modify the user and the password, I'm just going to start by trying to connect to MySQL using the MySQL exporter. So let me go and copy these values so that I don't forget them, because we know these we have to modify into our MySQL exporter values.yaml. All right, number one, if you want your exporter to monitor a specific database, you can include that database name here. I'm going to omit that. What is the host going to be? Well, we know MySQL is deployed inside of database monitoring. So I'm going to get the service by which the MySQL instance can be accessed. Excuse me. kubectl get service -n database monitoring. All right. here is the service name, MySQL, and you'll know if you took my Kubernetes course that we should be able to access this service by first specifying the host, which is the service name, followed by the port at which the service can be accessed. And that's pretty much it. So we can start by specifying the service name, MySQL. That's going to allow it to find the host that lives inside of the same namespace, because we're going to be installing the Helm chart in the same namespace. Additional config we don't need to touch. This I will modify later. This I will modify later as well. Port 3306. All right. Now, if our exporter is deployed inside of the same namespace as the MySQL instance itself, it should successfully be able to use this host and port to reach it, if you will. But if it lives in a different namespace, which it very well might depending on your setup, then what you need to also do is specify the namespace where the MySQL service is in. So that namespace is database monitoring. All right. Followed by the Kubernetes suffix service.cluster.local. This would also work if you're using OpenShift or something. All right. And so this is ideal because this will allow our exporter to connect to our MySQL instance, whether it's in the same namespace or a different one, unless you have some sort of network policy in place. So now what we can do is say kubectl, we can install a MySQL exporter. So this is what we're going to name the Helm release, which will be based on the Helm chart Prometheus community. If I remember correctly, the Helm chart was called Prometheus MySQL exporter. All right, -- namespace, database monitoring. So here I am going to indeed deploy it inside the same namespace as our MySQL service. And if we just deploy it like that, it's going to use the default values. We don't want it to do that. We want it to override some of these values with the custom ones we have here. So the values are inside of a MySQL exporter folder / MySQL exporter values.yaml. Unknown command. Oh my god, I'm such a doofus. This should be Helm install, not kubectl install. Sorry, guys. Going all the way back. I always hate doing this. All right, beautiful. Now, as promised, let me clear the output. If I say kubectl get pods -n, what was the namespace? Database monitoring. Now we see 2 pods, both of them running. Beautiful. A MySQL instance and a MySQL exporter that's constantly extracting metrics out of this instance. How can we make sure that this actually has metrics? Newsflash, it won't. And we can verify that by going to the endpoint where this exporter is going to expose all of the metrics that it scrapes from the MySQL instance. So I'm going to say kubectl get service -n database monitoring. All right. The service is going to expose all of the metrics that it manages to extract at the port 9104. So what I can do is do a port forward to see if there are any metrics. Service / MySQL exporter. Let me just copy it. So remember what I said, that this is all just a big puzzle. You deploy one thing, you see what's wrong, you troubleshoot, you go back, adjust more values until you get a deployment that works. All right, -n database monitoring. And I'm going to follow this with an ampersand so that it also runs in the background. All right. So now if I go and say localhost 9104, here I see the home page for the MySQL exporter. Okay. But I want to look at the metrics that it's exposing, which usually most exporters expose at a metrics endpoint. All right. And all I see is a bunch of Go related metrics, which makes sense because of the Prometheus exporter's Go environment around which it was developed. But we don't see any metrics relating to the MySQL instance that it's supposedly pulling metrics from. Why is that, you might ask? Well, this is where we debug. So now this is still running in the background. So what I can do is kill the port forward. And what this is going to do is kill the first process running in the background for this terminal session. All right, got killed. Let me clear the output. I'm going to say kubectl get pods again, -n database monitoring. All right, and now what I can do is play with some logs. So kubectl logs. We want to stream the logs for the following pod to see what the heck is going wrong. Oh, got to specify the namespace. So again, whenever you don't get the results that you want, look at the logs or describe the pod or whatever, but don't panic, just troubleshoot. And now we just simply need to scroll through it. So here we see it's literally the first thing we see. Level error source is equal to exporter error opening connection to database. So it found the database. It was able to find it. So now we know, come on. Why did I do this? Sorry guys, give me a second, I'm struggling. So now we know that the host allowed the exporter to find the MySQL instance, and it's able to access it at the port where it's allegedly serving requests, but it's being denied access. Why? It needs to authenticate. Okay, so right there, I know exactly why the exporter isn't able to grab any metrics. How can it authenticate? A username and a password. Now, you normally never want to specify a password in plain text. So what we're going to do, the user is fine. We can specify that in plain text. What is the username that the exporter is going to use? Again, so the secret specifies all of the credentials needed to authenticate against MySQL. This is the MySQL secret. Let's make sure that secret is deployed. kubectl get secret -n database monitoring. All right. And the MySQL user that can be used to authenticate against it. This is base64 encoded, but it's actually MySQL user, so we can modify that. And I just told you the password you never want to actually specify in plain text. Now you need to see if this exporter allows you to configure a value which can somehow leverage the password stored inside of the MySQL secret. If not, we have no choice but to use the password field. But ideally, I want to avoid that. So let's go back to the connection parameters. All right. Oh, there it is. Existing password secret. Pretending like I didn't search it up before this lesson, but yeah. Anyways, it does have it does have a value that we can modify to grab the name of the secret that is deployed, and once it gets the secret, what the key for the secret password is. All right. So we can go ahead and play with this. So what is the name of the secret? Well, I just got the secret and it's MySQL secret. What is the key that is referring to the password that we need to authenticate? MySQL password. All right. So what it's going to do is it's going to grab the password value, and now alongside the MySQL user, it will use this information to authenticate against MySQL. Simple as that. Will this work? Did we solve one piece of the puzzle? Let's find out. So we can go ahead and upgrade the Helm release that we currently have with the new values. So Helm upgrade. We can upgrade the existing MySQL exporter release. Specify the Helm chart again. Prometheus MySQL exporter. All right. We can upgrade the Helm release that was deployed in the namespace database monitoring with the new values inside of MySQL exporter / MySQL exporter values.yaml. Alrighty. Let me get a drink of water real quick. What to do now? So now we want to make sure. Let me clear the output. kubectl get pods -n database monitoring. Now we want to make sure that this is actually able to authenticate against MySQL and ideally be able to grab metrics from it. So kubectl logs-f for the following pod -n database monitoring. I don't see an error. Do you? I'm pretty optimistic. All right. I shouldn't have killed the earlier port forward. Let's clear the output. kubectl port forward. I do not remember the service name. kubectl get service -n database monitoring. kubectl port forward service / what am I doing? All right. Port forward, port 9104 to local machine port 9104 -n database monitoring. We'll run it in the background as well. Localhost 9104 / metrics. So notice now it's just a bunch of Go metric data that's specific to the exporter itself. Will we now have metrics for the MySQL instance? There you go. A whole bunch of metrics. I'm just going to kill what we have currently. Or you know what? Let's not kill it. Yeah, let's kill it. I'm going to kill it because I'm also recording and I only have a MacBook Air M1 and it's already starting to slow down. You can feel free to keep it. So now, the MySQL exporter is exposing all of this metric data at this endpoint. So now what we need to do is deploy a service monitor that tells Prometheus, hey, there are metrics being exposed at this endpoint. Can you please scrape them? And what we can do is, number one, deploy our own service monitor, which is very easy. Or number two, check if the exporter has a service monitor within its templates folder whose values we can configure towards a deployment that suits us. So it does have a service monitor.yaml. So what we can do is play around with the values inside of values.yaml in order to configure the service monitor for our purposes. So by default, the service monitor is not enabled. So what we need to do is enable it. I'm going to start by copying what we have inside of MySQL exporter values. Okay. And what do I need to fix? Enabled, true. All right. Additional labels. So this will depend on whether or not you installed Prometheus using the kube-prometheus stack. If you did install it using the kube-prometheus stack, then your service monitor, in order for it to be discovered, it needs to have the label release Prometheus. Because that's just how Prometheus is configured when deployed using the Kubernetes stack, it will only discover service monitors that have this label. So we give it that additional label. Okay. Job label, whatever. No need for that. Multiple target, no need for that. I feel like I might have deleted too much. So by default, the service monitor is going to have an interval of 30 seconds, a scrape timeout of 10. It will be deployed in the namespace monitoring, which is where my Prometheus instance is. I'm going to allow it to run there. It doesn't matter. All right, and that's all I really want to do. Okay. So now we can say kubectl, not kubectl, I keep making that mistake, Helm upgrade. I have the command somewhere. So now that also deploys a service monitor that's going to configure Prometheus to scrape the metrics exposed by this exporter every 30 seconds. And this allows the service monitor to be discovered by Prometheus. The service monitor is going to be deployed inside of the namespace monitoring by default, but that's fine. It doesn't have to be in the same namespace. I'm guessing that's it. It doesn't have to be in the same namespace as your exporter, because a lot of people make the mistake of thinking that it's the service monitor that's pulling metric data from the exporter. No, that's not what happens. The exporter is exposing all of this metric data, and the service monitor, all it does is it configures Prometheus to find the metric data exposed at this endpoint. So the service monitor is interacting with Prometheus, not directly with the exporter. It's Prometheus that pulls all of this data, okay? And how can we make sure this data is now in the Prometheus database? Well, since we also have Grafana connected to the Prometheus data source, by deploying this Grafana dashboard, if we see data, then effectively the data is inside Prometheus and we should be able to monitor it using a Grafana dashboard. Okay, so that's going to be our final step. I'm going to say kubectl, let me clear the output, kubectl apply -f Grafana, apply this dashboard inside of the monitoring namespace, because inside of the monitoring namespace I also have Grafana there as well. And what that's going to do is create a config map with the Grafana dashboard with the label 1. Grafana, when deployed using the Kubernetes stack, will automatically detect the dashboard with this label and import it. Okay, so now what I can do, first of all, I just want to prove to you that I do have Grafana deployed in that namespace. Get pods -n monitoring. Yeah, damn it. kubectl. All right, here I've got Grafana. Let me get the Grafana service, kubectl get service -n monitoring. All right, the service I want to port forward is the following. So let me copy this, clear the output, kubectl port forward, service Prometheus Grafana. We want to port forward it on our local machine port 3000. The cluster IP port, I believe, was 80. -n monitoring. Let's run this in the background, why not? So now we'll go ahead and say localhost 3000. Go to Grafana. And by virtue of following this tutorial, you also get a pretty cool, that's Postgres, that's for another lesson. Pretend like you didn't see that. MongoDB, where's the MySQL dashboard? All right, fast forward 5 minutes. There was an issue with the Grafana dashboard. This said Postgres, where it should initially be MySQL. I also had to delete a bunch of other conflicting dashboards that I had prepared for other lessons. But anyways, if you were watching this video, you should have been fine. If you see a bunch of metrics for MySQL, congratulations, you conquered the Prometheus exporter for MySQL. If you want to, feel free to look at all of the other values, see how they would suit your purposes, you're welcome to. But not only do you now know how to configure MySQL exporters to scrape MySQL instances and save that data to Prometheus, you also get a Grafana dashboard for free. All right, that's pretty much all I want to teach you for this lesson. If you go ahead and populate your MySQL instance with some dummy data, you should see some much cooler metrics that you can visualize. And I'm going to leave it at that. In the next lesson, I'm probably going to show you how to deploy the exporter for either Postgres, Mongo, or Redis. So I'll see you in the next one. Before we move to the next module, let's do some cleaning up. First, make sure that you're CD'd into the correct folder where you can directly access all the MySQL resources that we had, and then enter this command to remove all the MySQL resources that were created from files in the MySQL folder. Okay, and then just to make sure that we don't have any loose ends, enter this command in order to delete the namespace database monitoring. That's all. After MySQL, let's monitor another popular database, PostgreSQL in Module 7. I'm going to play the video now. Enjoy. In this video, you will deploy a minimalistic instance of PostgreSQL alongside a Prometheus exporter, which will extract metrics from PostgreSQL. Then we're going to configure Prometheus to grab these metrics and save them in its time series database so that we can finally access these metrics from Grafana and visualize them in a Grafana dashboard. This video is composed of 5 chapters, and before we dive into any of them, I need to list the prerequisites needed to continue with this video. Number 1, you should have Helm installed and set up on your machine. If not, please check out this article and then come back. Link is inside the video description. And number 2, you should have Prometheus and Grafana installed in your Kubernetes cluster. If not, please check out this video and then come back. Link for that is inside the description as well. And that's it. We can start with chapter 1. All right, let's party. I left you a link to the repository inside of the video description. Make sure that you go to it. Once you do, go ahead and clone this repo inside of whatever directory you want. I'm just going to clone it inside a desktop for convenience. All right, now what I can go ahead and do, oh, there's me, is drag the resources I just cloned. You can do it in whatever editor you want, it doesn't really matter. I'm gonna go ahead and spin up a new terminal session, and let's begin. All right, now the goal of this video is to have an instance of Postgres and an instance of a Postgres exporter that is scraping metrics from Postgres and exposing it at a particular endpoint, which will then be saved into Prometheus for us to visualize in Grafana. I know that was a mouthful, so let's take things step by step. So here I have the resources needed to deploy a very minimalistic instance of Postgres. If you already have Postgres deployed on Kubernetes, then no need to apply these resources. If you were just following along this Prometheus series, then we can deploy a very minimalistic instance of Postgres by applying all of the resources inside of the Postgres folder. All right. And all of these need to be deployed in a namespace called database monitoring. So we need to create this namespace first. kubectl create namespace database monitoring. All right. Let me go ahead and clear the output. Reapply all the resources. All right. So now if I say kubectl get pods -n database monitoring. All right, so now we have PostgreSQL running. How do we scrape metrics from it? That's going to be done using a PostgreSQL exporter that needs to run alongside it. We're going to deploy our exporter using a Helm chart. This Prometheus community Helm repo contains many Helm charts, one of them being the one that we need. So I left you this link inside of the video description. Please make sure to copy it so that we can go ahead and add this repository into our local Helm configuration. We're going to give this repository an alias by which we can easily refer to it. I'm just going to call the alias Prometheus community. You can call it whatever you want. And using this alias, I can search this repository to see if it has the Helm chart that I need to deploy my PostgreSQL exporter. Indeed, it does. It's right over here. And so now, how can I deploy this exporter such that it's configured to scrape metrics from my existing PostgreSQL instance? Well, if you took my Kubernetes course, which if you haven't, I highly recommend that you do, link is in the description, you'll know that Helm streamlines the deployment of very sophisticated software, in this case, the PostgreSQL exporter, because it abstracts away all of the configuration files that are needed to deploy the software, and it just gives you access to a values file with a bunch of default values which you can configure to achieve a deployment that works for you. So if you go to the official Prometheus community GitHub repo, go to Helm chart, and then specifically click on the Helm chart for this exporter, you'll notice it has a templates folder with a bunch of files needed to achieve a deployment. Abstracted away from us, all we have to do is configure the values inside of the values.yaml file. Upon deploying a Helm release, most of these values we're not going to touch, but we are indeed going to configure the connection parameters that are needed for the exporter to connect to our instance of Postgres. So it needs to specify a host that it can use to find our Postgres service. And once it finds the service, we need to tell it the port that Postgres is serving requests on. So this is the first value I need to customize, which I will do inside of my PostgreSQL exporter values.yaml file. So here we specify all of values that we're going to override, and whatever we don't touch, the default will remain. And so what should the host be? Well, first, let's think about the deployment that we have right now. I have a stateful PostgreSQL instance that's currently running, and the service provides internal access to our PostgreSQL instance. So we need our exporter to communicate with the PostgreSQL service, which has the name PostgreSQL. Now, usually this is enough, but in the event that the exporter isn't deployed in the same namespace, database monitoring, we also need to specify the namespace that our service is deployed in. In that case, database monitoring. And then you'll remember from my Kubernetes course that we follow that up with the default suffix service.cluster.local. All right, and once the exporter is able to find our PostgreSQL service, it needs to know which port it's serving requests on. So we can go ahead and modify the port parameter to be 5432, which it already is. Okay, very convenient. And now, once our PostgreSQL exporter connects to our PostgreSQL service, it's going to redirect it to the PostgreSQL pod, but it's going to be denied access unless we give it the credentials that it needs to authenticate against PostgreSQL. Well, this Postgres instance was configured to accept a username of Postgres and a password of password123, but they've both been base64 encoded, which doesn't really matter, because what we can do is modify the username and password that Postgres exporter will use to authenticate towards the target Postgres instance. The username, usually you can write in plain text, but if I'm given the option to grab credentials from a secret, I prefer doing that. So here I have the option to grab the username from a secret, which I prefer doing instead. So we're going to say user secret. All right. And the name of the secret, well, you can grab right over here, but what I want to do is say kubectl get secret -n database monitoring and grab the name from here. And now what I can do is grab the value based on a particular key. I know I can just grab the key from here, Postgres user. But just for the sake of mixing things up, what I'm going to do is say kubectl get, well, let me just rerun this command and then say output it as a YAML. And the key that will map to some value is Postgres user. And now I can grab the password in much the same way. Password secret. Oh, come on. All right. The secret name is PostgreSQL secret, same as this one. And the key I can grab directly from here, which will map to the password value that is needed to authenticate against our PostgreSQL instance. Now, if we deploy our PostgreSQL exporter using this configuration, in theory, it should be able to find our Postgres service, connect to our PostgreSQL pod, which is serving requests on this port, and be able to authenticate using the credentials that are configured in the Postgres secret. Will everything work? Let's find out. Let me clear the output. I'm going to install a new Helm release called Postgres Exporter based on the following Helm chart. And we can steer the deployment of our Postgres exporter using the values that we just configured, Postgres exporter / Postgres exporter values.yaml. And we're going to deploy it inside the same namespace as the Postgres instance itself, just to keep things simple, -n database monitoring. All right, and the deployment was a success. Let me clear the output and say kubectl get pods -n database monitoring. And now we've got two pods. We've got the PostgreSQL instance minding its own business, and we've got the Postgres exporter that's connected to the Postgres instance and is consistently making API calls to it, extracting metrics from it, metrics, statistics, and it's going to expose all of these metrics at its own endpoint where Prometheus can scrape. How do we verify this? Well, just like we use a service to access this pod, we use a service to access this pod. So kubectl get service -n database monitoring. All right, this is the service by which we can access the Postgres exporter. We need to forward its internal port to a host machine port. So kubectl port forward. The service is called the following, and we're going to forward its internal port 80 to a host machine port of 9187. All right, doesn't really matter. And this service is in the namespace -database monitoring. All right, now we can go to localhost 9187. And this is the home page for the Prometheus PostgreSQL exporter. If you see a page like this, then that means it's running fine, but is it able to actually grab metrics? So whenever an exporter grabs metrics from some target app, it usually exposes these metrics at its own metrics endpoint. Here we see a lot of Postgres metrics that it's probably grabbing from this instance. How do we make sure? Well, this is enough of a verification, but there's a particular metric that's interesting called PG up. So is Postgres up? A value of yes means PostgreSQL is up, and our exporter was able to determine that. Beautiful. Now, all of this data the exporter is exporting or exposing at this endpoint, how do we make sure it gets saved into Prometheus? Well, that's where a service monitor comes in. So do we have to deploy our own service monitor to configure Prometheus to find all of this metric data at the exporter's endpoint? Not really, because if you look inside the Helm chart, there is also a service monitor.yaml inside of the templates folder, which means we can steer the creation of that service monitor by modifying some of the values inside of this values.yaml file. The only thing we need to really do is say service monitor enabled true. And one more thing. So if I say service monitor enabled true, that should therefore enable the creation of a service monitor. And now I want to set labels for the service monitor. The label that I need to add is, for my specific case, is release Prometheus. And the reason being is I deployed Prometheus using the Prometheus stack. And under that installation, Prometheus is configured to only discover service monitors that have this label. All right, and that's really all I need to do. This will ensure that a service monitor is created and that configures Prometheus to find all of the metric data being exposed at this endpoint. And once Prometheus finds this data, it's going to constantly pull it every 20 or 30 seconds and save it into its database. So now we need to upgrade the Helm release to use these new values. So I'm going to clear the output and I'm going to say Helm upgrade. If you remember, I called the Helm release Postgres exporter and I created the Helm release based on the following Helm chart. Now we're going to use the updated Postgres exporter values, -n database monitoring. What the heck? Oh, sorry guys. All right, beautiful. Let me clear the output. Let me make sure that a service monitor was indeed deployed. -n database monitoring. Beautiful, 11 seconds ago. And this service monitor, however it was created, it's currently configuring Prometheus to discover the metrics being exposed by this exporter. So now all of this metric data should be inside of Prometheus. And because we installed Prometheus and Grafana using the Prometheus stack, Grafana automatically has access to the Prometheus data source. So if we deploy this Grafana dashboard, we should see a bunch of PostgreSQL data inside of it. So let's say kubectl apply -f this Grafana dashboard. All right. And then what I can do is say kubectl get services -n monitoring because that's where my Grafana service is. And I'm going to port forward Prometheus Grafana. kubectl port forward the service Prometheus Grafana from port 80 to port 3000 of my local machine. -n monitoring. All right, so now if I go to localhost 3000, and we don't see the PostgreSQL dashboard, and let me explain why. Where did I deploy the dashboard? Did I even deploy it yet? I deployed the dashboard inside of the default namespace. It needs to go inside of the same namespace that Grafana is deployed in. In this case, I have my Grafana deployment inside of the namespace monitoring. And what's essentially going to happen is this label Grafana dashboard 1 allows Grafana to automatically detect this dashboard and import it. So now if you go ahead and apply the same steps, Grafana should now detect the dashboard. There you go. And the fact that we don't see any data in this dashboard, the reason you saw data is because I was running this tutorial an hour ago. And we don't see data in the past 5 minutes. It could just be that Prometheus needs time to scrape this data. We can verify this by accessing the Prometheus UI itself. So let's clear the output. kubectl get services -n monitoring. I want to access the Prometheus UI. So kubectl port forward service /Prometheus operated. We'll
keep the ports consistent. -n monitoring.
So let's go ahead and say localhost in 9090 and ensure that there is Postgres data. Indeed, there is. I see a lot of Postgres metrics. PG up. Let's execute that. It's set to 1. Everything is working fine. So I wonder why we don't have any data inside of the Grafana dashboard. Let me go ahead and report forward that, but I'm going to start port forwarding in the background because I'm tired of starting and stopping stuff. So port forward Prometheus in the background, port forward Grafana in the background. All right.
Let's try this again. I wonder why we're not seeing... Oh! I just needed to be patient. Sorry, guys. So, at least now you get to see that
All the data is indeed being saved into the Prometheus database.
and Grafana, which is connected to the Prometheus data source, is able to grab all the metric data and allow us to visualize it in a Grafana dashboard.
And so by watching this video, you learned how to configure a PostgreSQL Prometheus exporter
To discover an instance of PostgreSQL, extract metric data from it, expose it at a particular endpoint, which Prometheus can pull and save into its time series database, which Grafana can then connect to the Prometheus data source and allow us to visualize those same metrics in a Grafana dashboard. That's all for this video. In the next one, you're going to learn how to monitor a Redis dashboard or MongoDB, depending which one I end up doing.
So I'll see you in the next one. Before we move to the next module, make sure that you're CD'd into the correct folder where you can directly access all of your PostgreSQL resources, and then enter this command in order to delete all of the resources that were created from files inside of the PostgreSQL folder. And then once you're done, just to tie up any loose ends, remove the namespace database monitoring. And that's it. I'll see you in the next one. Next up in our database monitoring series is MongoDB in Module 8. I'm going to play the video now. Enjoy. In this video, you will deploy a minimalistic instance of MongoDB alongside a Prometheus exporter, which will extract metrics from MongoDB. Then we're going to configure Prometheus to grab these metrics and save them in its time series database so that we can finally access these metrics from Grafana and visualize them in a Grafana dashboard. This video is composed of 5 chapters, and before we dive into any of them, I need to list the prerequisites needed to continue with this video. Number 1, you should have Helm installed and set up on your machine. If not, please check out this article and then come back. Link is inside the video description. And number 2, you should have Prometheus and Grafana installed in your Kubernetes cluster. If not, please check out this video and then come back. Link for that is inside the description as well. And that's it. We can start with chapter 1. All right, let's begin. I left you a link to this repository inside of your video description. Make sure that you go to it so that we can clone the repo into whatever directory you want. I'm going to clone mine into desktop for convenience. All right, and I'm going to go ahead and launch the following folder that we just downloaded. You can launch into whatever editor you want, doesn't really matter. Let's spin up a new terminal. And what I've got over here inside of the MongoDB folder is a very minimalistic setup to install an instance of MongoDB. If you already have a MongoDB deployed in Kubernetes, no need to apply these resources. But if you were just following along this playlist, then we can go ahead and apply all the resources inside of this folder. And these are all going to be applied inside of a namespace called MongoDB. I already had a namespace called MongoDB, but if in case you didn't, then you should write the command kubectl create namespace MongoDB. All right, and then reapply the resources. In any case, if I say kubectl get pods -n MongoDB, I have an instance of MongoDB that's currently running. It's been running for 9 days apparently. I didn't know I had it running for that long, but whatever. And so what I want to do now is deploy a MongoDB exporter alongside this MongoDB instance that's going to extract metric data from it. How am I going to do that? Well, usually Prometheus exporters are deployed to Kubernetes using Helm charts. The Prometheus Community Helm repo is what contains all of the Prometheus Community Helm charts, so we need to add that to our local Helm config. I left you this link inside the video description. Make sure to copy it. Then go back here and say Helm repo add the following repository. Before we add this repository, we need to give it an alias by which we can easily refer to it. I'm just going to call it Prometheus Community. You can call the alias whatever you want. And now we can use this alias to search this repository and see what Helm charts it contains. And the exporter, the Helm chart we're specifically looking for, is the one that we're going to use to deploy the MongoDB exporter. Beautiful. So if you took my Kubernetes course, which you haven't, highly recommend that you do. Link is inside the description. You'll know that a Helm chart is used to streamline the deployment of very complex and sophisticated software, because all of the deployment files and configuration templates, they're all hidden away and abstracted into a templates folder. And the Helm chart essentially gives you access to a values file with a bunch of default values, and you can choose which values you want to modify to steer your Helm deployment towards one that works for you. So whenever deploying a Helm chart, it usually boils down to being a puzzle of knowing which values you need to customize in order to achieve the deployment that you want. So if we go to the Prometheus Community GitHub repo, which has all of the Helm charts for various exporters, let me go to that. The Helm chart we're interested in is the MongoDB exporter Helm chart. Here we see the templates folder that has all of the different configuration files hidden away. Not that many files actually, a fairly simple deployment. But all we need to play around with is the values inside of the values.yaml file. This values.yaml file contains a bunch of default values, most of which we don't need to touch, but there are some values that we need to override inside of our own values.yaml file. So let me actually just copy the comment in as well. So the exporter is going to use this URI to try to connect to our instance of MongoDB. It needs to connect to a MongoDB service called MongoDB. So the host is already halfway correct, but we also need to specify the service, the namespace that service is in, just in case the exporter is deployed in a different namespace. And if you took my Kubernetes course, you'll know that we need to follow that up with the default Kubernetes suffix service.cluster.local. So this whole thing is the host. The host tells the exporter where to find the MongoDB service. And once it finds the MongoDB service, the port tells the exporter where the service is serving requests. All right. Now, will this be enough for our exporter to connect to MongoDB? Yes. However, upon connecting to MongoDB through this service, MongoDB is going to deny any requests made to it because it requires a username and password for authentication. So we also need to include the following into our URI. We can do it as described in this comment. So followed by the scheme, we're going to specify the user, which in the secret was base64 encoded, but we can write it in plain text over here. Admin followed by the password, password123, and then followed by an @ All right. Where's the @ symbol? Right over here. Now, will this work? Is this enough for the exporter, once deployed, to be able to connect to the MongoDB instance and constantly flood it with requests in order to extract metrics out of it? Let's find out. Let's clear the output. So now we can go ahead and Helm install. We can call the Helm release MongoDB exporter. We're going to install a MongoDB exporter based on the following Helm chart. But we're not just going to use all of these default values. Some of them we're going to override using our own values.yaml file. So -f, the folder is MongoDB exporter. The file is the following values.yaml file. And we're going to deploy this exporter inside the same namespace as MongoDB itself, which is the namespace MongoDB. All right, we're in business. So now let me maximize the following. If I clear the output and say kubectl get pods-n MongoDB, I've got MongoDB currently running. The exporter is running, but it's not ready yet. So let's give it some time. All right, that's enough time. Cool. Is this exporter actually extracting metrics from MongoDB? Let's find out. What I'm going to do is get the service by which this exporter can be accessed. So get service-n MongoDB. We've got two services, one used to access this pod, one used to access this one. We need to forward the internal port of this service to a local machine port. So kubectl port forward. We want to forward the port of this service from the internal port 9216 to a similar host machine port 9216. And we'll run this port forward in the background just so that it doesn't stop if I cancel the thing. Services MongoDB exporter not found. Oh, I got to specify the namespace database the namespace that it's in, MongoDB. Interesting. kubectl get services-n MongoDB. kubectl port forward the service, which is the following. Oh. Let's do that. Okay, beautiful. So if I go to localhost 9216, so here's our MongoDB exporter. It's been deployed. That's the UI for the home page. In theory, it's extracting metrics from MongoDB. And where is it storing these metrics? At its own metrics endpoint. And if I refresh, I should see more metrics. All right. So one metric that's really interesting is MongoDB up, because it confirms that the MongoDB instance itself is running and healthy, and the exporter was able to extract that metric out of it, among many, many other hundreds of metrics. All right. Now, our exporter was able to successfully use this URI to connect to our MongoDB instance through the following service, but I don't like that the password is being hard-coded in plain text. If there is some way that we can rely on a value which can pull the password from a secret, that would be great. So what can we modify over here? Remember that when you're working with Helm charts, it all comes down to being a puzzle where you have to find values to change and know how to change them. So this one's interesting. Existing secret. So what you can do here is have the exporter look for a secret with a particular name and reference the URI in that secret. So instead of specifying the URI as follows, what I want to do is tell it, hey, there's a secret inside of the namespace MongoDB. What is that secret called? MongoDB secret, consistent with the one that we just deployed. All right. And the secret has a key, in this case, called connection URI that maps to the same URI that we had earlier. In this case, it's base 64 encoded, okay? So now, instead of specifying the URI with the password in plain text over here, we're referencing an existing secret in order to grab the connection URI as follows. This should work the exact same way. All right, we're going to grab the exact same metrics. Everything is going to work out. But then these metrics being exposed by the exporter at this endpoint, how do we configure Prometheus to find this metric data and save it in its Prometheus database? Do we deploy our own service monitor? We could, unless the exporter Helm chart already contains a service monitor.yaml file, which it does, whose creation can be steered by modifying the values inside of the values.yaml file. So if we go to the service monitor section, one of the values is set to enabled false. Obviously, we just kind of need to set that to true. And that's pretty much it. Let's copy all of that for now. We'll set enabled to true. These we don't really need to touch. All right. Scrape timeout, scraping interval, doesn't really matter. We can leave them, it's okay. Now the only thing I do need to add is an additional label, release Prometheus. The reason is I installed Prometheus and Grafana using the Prometheus stack, and my Prometheus instance is configured to only discover service monitors that have this label. You need to adjust this if your Prometheus operator uses a different label, but if you installed Prometheus using the Prometheus stack like myself, this should be sufficient. All right. And if you want to make sure that the deployed service monitor is able to save data into Prometheus, let's first upgrade this Helm chart to use these new values. So Helm upgrade, we need to upgrade the Helm release MongoDB exporter, which was created based on the following Helm chart, to use these new values. We're going to use a secret to grab the connection URI, and we're also going to enable the creation of a service monitor this time. So let's grab the values from the following values.yaml file, and we're going to upgrade this in the namespace MongoDB. Wait, how is this even working? My indentation is totally off. This should be at the very beginning. Okay. Should be fine now. Let me do a Helm upgrade again. Clear the output. So now the configured exporter is extracting. So now the configured exporter is grabbing the connection URI from the existing secret, and we can ensure that the metrics are still being saved by saying kubectl get service -n MongoDB. We'll do a port forward again because I feel like whatever we had before was killed off. So kubectl port forward service / the following -n. We'll do the port mapping first. -n MongoDB, running it in the background. It was already running, so let's kill off the previous one. Kill %1, kill in the first job in the current session. Terminated. All right, let's do it again. Localhost 9216/metrics. All right, we've got all these metrics. And there should also be a service monitor, kubectl get service monitor -n MongoDB. We see a service monitor as well. The service monitor is going to get discovered by Prometheus, and it's going to configure Prometheus to find the data being exposed by this exporter at this particular endpoint. So Prometheus is constantly pulling this data now every 30 seconds. All right. Now what I want to do is say kubectl get services -n monitoring. Here we see the service for the Prometheus instance. All right. What I want to do is do a port forward and check and see if all this data is being saved there, because the service monitor would have configured Prometheus to find the data exposed at this endpoint. So kubectl port forward the following service, 9090, 9090, -n monitoring, ampersand, so I can run in the background as well, localhost 9090. All right, let's check for one of the metrics. My go-to is MongoDB up. If we get a value of 1, then, or if we get any value at all, then everything should be fine. Empty query result. It's going to take at least 30 seconds for the data to get pulled into Prometheus at least the first time around. Let me copy the whole thing. Kind of weird. I don't really get why this is happening. Oh, there you go. The metric is there. All right, so now all this data is being pulled into the Prometheus database. And if you have the same configuration as me, where Grafana is connected to the Prometheus data source, then by deploying this Grafana dashboard, we should see it populated with a lot of MongoDB data. So let's try this out. kubectl apply. Let me clear the output so that you're not looking at the bottom of my screen. kubectl apply -f, the resources inside of the Grafana folder. We want to deploy this config map in the namespace MongoDB. No, in the same namespace as where Grafana is currently in, because I already had the dashboard deployed, but whatever. Grafana, it's going to see this label on this config map, which will allow it to auto-discover this dashboard and import it. All right, so now if I say kubectl get service -n monitoring, I want to go into the Prometheus Grafana service. So kubectl port, let me increase this, port forward, service. We'll do the port mapping first, 3000 internal port 80 -n MongoDB. We'll run this in the background as well. Services Prometheus Grafana not found. Oh, wrong namespace. All right, we'll go to localhost 3000. MongoDB dashboard. Beautiful. MongoDB service is currently up. Current connections, active connections. So by following this video, you learned how to configure a Prometheus exporter to discover a MongoDB instance, scrape metrics from it, expose those metrics at a particular endpoint, which are then saved into a Prometheus database, which allows Grafana to visualize these metrics in a cool, nice Grafana dashboard. And you also get a Grafana dashboard for free. All right, and that's pretty much it for this lesson. Before we wrap up, I think we should do a final cleanup. So we'll clear the output. We'll start by uninstalling the exporter, helm uninstall MongoDB exporter -n MongoDB. Now the exporter was uninstalled. We can delete the namespace MongoDB. We'll delete every resource that was created from each file in MongoDB. So -f MongoDB. We'll delete every resource that was created in the MongoDB namespace. Now we can go ahead and delete the namespace itself. Or sorry, we can delete the Grafana dashboard. Delete Grafana -n monitoring. Sorry, delete -f. delete all the resources that were created from files in this folder. All right. And now if you want to remove the Helm repository as well, you can say Helm repo, remove Prometheus community. All right, and we are done. Final step, delete the namespace, kubectl, delete namespace, MongoDB. And it's like we never did anything. All right, in the next lesson, I'm going to show you how to do the exact same thing, but for Redis. I'll see you then. For our final module, we'll complete our database monitoring journey with Redis. I'm going to play the video now. Enjoy it. In this video, you will deploy a minimalistic instance of Redis alongside a Prometheus exporter, which will extract metrics from Redis. Then we're going to configure Prometheus to grab these metrics and save them in its time series database so that we can finally access these metrics from Grafana and visualize them in a Grafana dashboard. This video is composed of 5 chapters, and before we dive into any of them, I need to list the prerequisites needed to continue with this video. Number 1, you should have Helm installed and set up on your machine. If not, please check out this article and then come back. Link is inside the video description. And number 2, you should have Prometheus and Grafana installed in your Kubernetes cluster. If not, please check out this video and then come back. Link for that is inside the description as well. And that's it. We can start with chapter 1. All right, let's get to work. I left you a link to this GitHub repo inside of the video description. Make sure that you go to it so that we can go ahead and clone this repo into whatever directory you want. I'm going to clone it inside of desktop for convenience. All right. And there's me who's about to open Visual Studio Code, load in the folder we just downloaded. You can use whatever editor you want, doesn't really matter. Go ahead and spin up a new terminal, and let's begin. All right, and if you already have Redis deployed in your Kubernetes cluster, then no need to apply these resources. But if you're simply following this Prometheus playlist, then what we're going to do is deploy Redis using this very minimalistic setup, where each resource is expected to be deployed inside of the namespace database monitoring. So kubectl, create namespace, make sure that you have this namespace created so that we can deploy all of these resources there. kubectl apply all of the resources inside of the, apply all the configurations inside of the Redis folder. Doing that in the namespace database monitoring. All right, so what this does is it creates a stateful instance of Redis that can be accessed using the following service, and once accessed, authenticated using the following password. Let's clear the output, and we'll say kubectl get pods-n database monitoring. We have this Redis instance, and what we want to do is alongside this Redis instance, deploy a Redis Prometheus exporter that constantly makes API calls to this Redis instance, extracts metrics from it, and exposes these metrics at a particular endpoint. How are we going to deploy an exporter? We're going to use a Helm chart. So this Helm repository, whose link I will leave you inside the video description, make sure to copy it. This Helm repository contains many Prometheus exporters, one of them being the Redis exporter. So copy this link so that we can add the repo to our local Helm configuration. We can use an alias by which we can refer to the repo. We'll call the alias Prometheus community. You can call the alias whatever you want, and it will be an alias for the following Helm repo, which we're about to add. All right, and once added, we can search this repo for Helm charts, specifically the Redis Helm chart that we're going to use. All right. Now, if you are signed up to my Kubernetes course, if you're not, link is inside the description. Highly recommend you check it out. If you were following my Kubernetes course, then you'll know that a Helm chart streamlines the deployment of very complicated software, because what it does is it abstracts away all of the configuration files inside of a templates folder and leaves you with a values file with default values that you can configure to steer the Helm chart deployment towards one that suits your purposes. So if I go to the official Prometheus community GitHub repo that has a bunch of Helm charts, I'm going to go down to the Helm chart that allows us to deploy a Redis exporter. All of the configuration files needed to deploy the Redis exporter are hidden away inside of the templates folder, and the only things we need to modify are the default values inside of this values.yaml file. Okay, so whatever values we don't want to touch, we don't touch, and the values we want to customize, we're going to do right over here inside of this exporter values.yaml file. So first things first, when the Redis exporter is deployed, it needs to be configured such that it can connect to the right Redis address, the Redis address that will lead it to connect to the following Redis instance. Now, this Redis instance can be accessed through the following Redis cluster IP service. So the host in this case is not MyRedis, it's Redis. All right, but we're not done specifying the host just yet, because in case the Redis exporter is deployed in a different namespace than the Redis instance itself, then we'll need to specify the namespace that the Redis service is in. All right, and to finalize our host, we use the Kubernetes suffix service.cluster.local as you learned in the Kubernetes course. And this host will allow the Redis exporter to find the Redis service, and the port will tell it where the Redis service is serving requests. And upon connecting to the Redis instance through the Redis service, Redis is going to require it to authenticate using the following Redis password. Now, to my knowledge, Redis by default only requires a password. The username is optional, and I think that was added in Redis 6.0. But anyways, we need to give the exporter the following password in order for it to authenticate to Redis once it's been connected to it. So what value will we have to modify in the values.yaml file? Let's look through it. Is there a section for authentication? So that's the thing with deploying Helm charts. You want to leave the values that aren't relevant to you and only modify the values that need to be modified. And there you go. Authentication. We need to enable that so that it's true. And we can use a secret in order to reference the Redis password. That's pretty much it. We'll set that to true. The secret, we can say kubectl get secret -n database monitoring. The secret is called Redis secret in accordance to this YAML. And the key that maps to the password is Redis password. You can also obtain this by saying get secret -o YAML, output the YAML from which this resource was deployed, and you'll get the same thing as what we have over here. Anyways, doesn't really matter. So now the Redis exporter has what it needs in order to find the Redis service. And once the service connects it to the Redis instance, it has the credentials it needs to authenticate. I think we're ready to deploy our exporter. So now we'll clear the output and we're going to say Helm install. We're going to install a Redis exporter, and this Helm release will be based on the following Helm chart. All right. The exporter is going to be deployed not just with these default values, but with the values that we modified inside of the following file. So -f Redis exporter / Redis exporter values.yaml. Okay. And we're going to deploy it inside the same namespace as our current Redis instance, so database monitoring, which means we didn't need to specify the complete fully qualified host. We could have just done this in this case because they're in the same namespace, but doesn't harm to make this configuration more flexible. And what else do I need to add? I think that should be it. All right, now we'll say kubectl get pods dash n database monitoring. We should now have 2 pods. One pod is the Redis instance. The other pod is the one that connected to this Redis instance through the cluster IP service at the particular port, authenticated to it, and is now probably constantly making API calls to Redis, extracting metrics out of it and exposing all of these metrics at its own endpoint. So how do we access the metrics that the Redis exporter is currently extracting? Well, to access the exporter, we need to do it through its own service. So kubectl get service -n database monitoring. We want to access it through the following service. So kubectl port forward will port forward this service's cluster IP port to a local machine port. So we'll do the port mapping right over here. We need to specify the namespace that the service is in. And we'll run this port forward in the background using the ampersand. All right. So is this exporter actually pulling metric data? Let's find out. Localhost 9121. 9121. This is the home page for the Redis exporter. And this is where it exposes all of the metrics that it's scraping from the Redis instance. All right, and we have all of these Redis metrics, which means our exporter was able to successfully consistently make API calls to this instance and grab metrics from it. It's doing that in real time. Now we have all of these Redis metrics. How do we save them inside of the Prometheus database? So if you were following along in this playlist, you'll know that I have Prometheus deployed in the monitoring namespace alongside Grafana. And in order to save all of these metrics to the Prometheus database, I need to configure Prometheus to find this metrics endpoint. And we can do that through a service monitor. Do we need to deploy our own service monitor? Let's find out. Does the Prometheus Redis exporter Helm chart contain a service monitor YAML? Yes, it does. And we can steer the creation of this service monitor by modifying values inside of the values.yaml file. So we can go to the service monitor section, which is right over here. Modify what we need to modify inside of our Redis exporter values.yaml file. So we need to enable its creation. That's really important. We'll set that to true. And the only other thing we really need to do is add an additional label. We need to set a label for the service monitor of release Prometheus. All right, this label is going to be sent over to the service monitor YAML. That's going to give it the following label. The reason we're doing that is because I deployed Prometheus using the kubeprometheus stack, and it's configured to discover service monitors that have the label release Prometheus. Now, if you didn't deploy Prometheus using the kubeprometheus stack, then chances are you won't even need this label. But anyway, now we can upgrade our Helm release to use these new values, because now this will enable the creation of a service monitor. So let's clear the output and we'll say Helm upgrade. I believe the Helm release was called Redis exporter, which we created based on the following Helm chart -f. The upgrade will occur based on the values, the updated values inside of Redis exporter values.yaml. And we'll make sure to perform the upgrade inside of the same namespace. All right. So now not only do we have Redis connected, not only do you have the Redis exporter connected to our Redis instance, we should also have a service monitor inside of the same namespace. So get service monitor monitor-n database monitoring. All right, and this service monitor is going to get discovered by Prometheus, and it's going to configure Prometheus to discover all of the metrics being exposed by this exporter, which means Prometheus is now going to be constantly pulling this data every 30 seconds, saving it into its own database. How do we confirm this? Well, I've got Prometheus deployed inside of the namespace monitoring, which means it should also have a corresponding service at which it can be accessed. So kubectl get service-n monitoring. You probably have Prometheus deployed in the same namespace as well. That's the monitoring namespace is pretty standard. If you're using OpenShift, it's OpenShift monitoring. But anyways, let me clear the output and run this again. We want to access Prometheus, make sure the data is being saved there. So kubectl port forward service/Prometheus operated. The Prometheus UI can be accessed at the cluster IP port 9090, which we can map to a local machine port 9090. Got to specify the namespace. Sorry, the namespace that the service is in is monitoring, followed by an ampersand so that this runs in the background so that it doesn't stop. Localhost 9090. In the Prometheus UI, if I paste in any of these metrics, let me try one that's more intuitive. Redis up. If I paste this in, I get a value, meaning that all this data is being saved into Prometheus. Now, because I deployed Prometheus using the kubeprometheus stack, I've also got Grafana, and Grafana is connected to this Prometheus data source. So if I deploy this Grafana dashboard inside the same namespace as Grafana itself, Grafana is going to be able to detect that this is a Grafana dashboard because of this label and import it. And I should be able to see data inside of this dashboard. So let's try it out. So kubectl apply-f the following Grafana dashboard inside of the same namespace as where Grafana is in. And now we can port forward the service that allows us to access the Grafana UI. So we'll say kubectl port forward service/Prometheus Grafana. We'll use the local machine port 3000 to map where it's exposed at this internal port -n monitoring. We'll run that in the background as well. All right, localhost 3000. We should see a dashboard for Redis. Redis dashboard. Beautiful. The fact that we see data means all the queries being made in this Grafana dashboard are being made to the Prometheus database that has all of this metric data, and we can visualize all of that data in this very nice and beautiful dashboard. So by following this tutorial, not only do you now know how to configure a Redis exporter to connect to a Redis instance and scrape metric data from it, you also get this Grafana dashboard for free. And now before we finalize this video, what I want to do is perform a final cleanup. You know, just in case you were watching this video for tutorial purposes, you don't want all this stuff running in the background. So we'll start by killing off all the processes we have. So kill %1 to kill the first process within this current terminal session. All right, we'll say kill %2. That kills the Prometheus port forward, kill %3. Okay, now we'll Helm uninstall the Redis exporter release that was deployed in the namespace database monitoring. Now we'll kubectl delete all of the resources that were created from the files in this folder. -n database monitoring. kubectl delete the resource that was created from the file in this folder, -n monitoring. That'll delete the dashboard. If you want to remove the Prometheus community from your Helm config, you can do that as well. And then we can end things off by deleting the namespace database monitoring, which will delete the namespace and pretty much everything inside of it if we happen to miss something, and we are done. If you enjoyed this course and want to deepen your understanding of Kubernetes, check out my Kubernetes Bootcamp, Conquer Kubernetes from Zero to Cloud. You'll learn how to deploy and manage cloud-native applications at scale, which is a skill that's very high in demand at companies across every single industry. I hope to see you in there.